Hi everyone and welcome to the course. In this series we're going to dive deep into TypeScript and I will show you how to build robust and scalable applications as well as modern design patterns. My name is Martin Yanev, a software engineer and a computer science professor at Fitchburg State University, and I will be your instructor for this course. Also keep an eye for this icon, it will be shown a few times throughout the course, and if you can tell me how many times it shows up in the video, you will have a chance to win a completely free digital copy of my new book, Building AI Applications with the OpenAI APIs. This course is suitable for beginners and we're going to start with the very basics. Then we will move to creational, structural, behavioral design patterns like Singleton, factory, adapter, observer, and more. We will cover functional and reactive programming, also UML diagrams, as well as best practices to write maintainable and clean code on TypeScript. By the end of the course, you will have the skills to design enterprise-grade applications, refactor legacy JavaScript into TypeScript, and apply patterns confidently in real-world scenarios. You'll also find the full code from this video in a GitHub repository linked in the description. Also watch this video until the end, because in the end of the course I will give you a final project where you will be able to test everything you learned. The final project is also going to be added inside the GitHub repository so you can access it from there. Now please like this video and subscribe to my channel for more completely free courses like this one. And now let's get started.
Now let's delve into TypeScript, a powerful extension of JavaScript that incorporates static types, offering enhanced security and improved developer experience. TypeScript 5, the latest version, introduces various new features, enhancing type safety and optimizing performance. By mastering TypeScript, you're not just learning a new programming language, you're equipping yourself with the tools to write cleaner, more maintainable code. Now let's examine a simple function in JavaScript that multiplies two numbers. The function named multiply takes two parameters and returns their product. However, JavaScript's dynamic typing allows any data types to be passed, which can lead to unexpected outcomes. For instance, if we pass strings representing numbers like 5 and 4, instead of performing numeric multiplication, JavaScript performs string concatenation, resulting in 54. This demonstrates a key pitfall of JavaScript's dynamic typing system. Now let's see how we can implement the same function in TypeScript. In this version, we explicitly define the types of the parameters as number and specify that the function returns a number. This strong typing ensures that if we attempt to pass strings instead of numbers, TypeScript raises a compile time error. This way, developers can catch potential bugs early in the development process, greatly enhancing the reliability and robustness of the code. Through this example, it's clear how TypeScript's type system provides a safeguard against common runtime errors found in JavaScript. Now let's see how we can declare and utilize basic types in TypeScript. The first line demonstrates how to declare a variable called name, which is explicitly typed as a string and assign the value Alice. This approach ensures that name will always hold a string value, providing clarity and preventing inadvertent type errors. Following that, we have the age variable, set as a number with the value of 30, again reinforcing strict typing for numeric data. Lastly, the variable isStudent is defined as a Boolean, initialized with the value true, indicating a student's enrollment status. This strong typing not only communicates intent, but also aids in detecting errors during the development phase. Next, we will write about defining complex types, such as arrays and tuples. In the second part, the code illustrates how to create an array of numbers with the variable scores, which holds homogeneous numeric values. TypeScript's typing system ensures that only numbers can be included in this array. Meanwhile, the user variable is a tuple, which effectively combines a string and a number, representing a user with a name and age. This structure strengthens type safety and ensures that each index adheres to its defined type, minimizing the risk of runtime errors when accessing these values. Now let's look at how to define and use enums in TypeScript, which allow you to work with a set of named constants. The code begins by declaring an enum called color that includes three members, red, green, and blue. Enums automatically assign integer values to their members, starting from 0, so red becomes 0, green becomes 1, and blue is 2. Following the enum definition, we create a variable named myColor of type color and assign it the value color green. This assignment gives myColor a meaningful name instead of a bare number, enhancing code clarity and making it easier to understand what color is being referenced. Finally, when we log myColor to the console, it outputs 1, which is the numeric representation of color, green. By using enums, we maintain a clear and maintainable codebase, leveraging descriptive named constants instead of arbitrary numeric values, which ultimately improves readability and reduces potential errors. Now let's take a look at how we can define a user object with TypeScript using interfaces. An interface, like the one we have for a user, establishes a contract for the object structure. It specifies what properties the object must have and their respective types. In our example, the user interface mandates that any user object should have a name of type string and an age of type number. Importantly, we see an optional property, phone, which implies that the phone number may or may not be present. This optionality provides flexibility, allowing the user object to be created without a phone number while still adhering to the interface's requirements. Next, we implement the user interface by creating a constant object named user. This object includes a name and age, demonstrating compliance with the interface. It's essential to note that since the phone property is optional, we can choose to include it later or omit it entirely, thus enhancing type safety without sacrificing functionality. This illustrates how interfaces not only define structure, but also promote clearer, more maintainable code. Now let's take a look at a powerful feature of TypeScript called generics, which allows us to write flexible and reusable functions while maintaining type safety. In this example, we'll create a generic function named firstElement that takes an array of any type as an argument and returns the first element of that array. To define this function, we use the syntax T, which indicates a type parameter that can represent any type. This means when we later call this function with different types of arrays, TypeScript will ensure that the type remains consistent and safe. For instance, we can pass an array of numbers and an array of strings to the same function. Once we declare our arrays, numArray for numbers and strArray for strings, we can call the firstElement function with each array. The function retrieves the first item from the specified array while TypeScript checks that we are using the function correctly according to the type we passed. This enhances code reusability, as the same logic applies to any type of data, eliminating the need to write separate functions for different data types. Overall, generics significantly improve code maintainability and flexibility. Now let's take a look at how TypeScript enhances the handling of enums. In the code snippet, we define an enum called direction with 4 members, up, down, left, and right. Enums in TypeScript are a great way to create a set of named constants, which improves the clarity and maintainability of your code. Each member of the enum is assigned a numeric value, starting from 0 by default. Next, we declare a variable named direction of the direction type and initialize it with direction, up, indicating that the current direction is up. This type-safe approach guarantees that direction can only assume values defined in the direction enum. If we attempt to assign a numeric value, such as 5, directly to the direction variable, TypeScript's compiler will throw an error. This error occurs because 5 is not a valid member of the direction enum. Hence, this feature enhances type safety by ensuring that misassignments are flagged early, allowing developers to write more predictable and reliable code. Now let's take a look at a practical application of decorators in TypeScript. We begin by defining a decorator called log, which is designed to intercept method calls and log their parameters to the console. This is achieved by taking advantage of the target, property key, and descriptor parameters that the decorator function receives. Inside the decorator, we store the original method and create a new function that first logs the method name and its arguments. Then it calls the original method using apply, ensuring we maintain the correct this context and pass the arguments along. Next, we implement a class named calculator. Within this class, we declare an add method, which is where we apply our @log decorator. By doing this, every time we invoke the add method, the parameters we provide will be logged automatically. Finally, we instantiate the calculator class and call the add method with 2 numbers, leading to a log statement in the console displaying the method name and the supplied arguments. This feature is particularly useful for debugging, as it allows developers to trace method calls and gain insights into application behavior in real time. TypeScript's recent enhancements to the development environment aim to facilitate a smoother experience. The streamlined module resolution process simplifies how modules are located and imported, bolstering productivity. With TypeScript 5, the integration with popular tools like Visual Studio Code is robust, offering powerful features like code completion and refactoring, ensuring developers can leverage TypeScript's capabilities effectively. As we wrap up our introduction to TypeScript, it's essential to highlight its advantages. The first and foremost is type safety, which leads to fewer runtime errors, clearer code, and better collaboration and communication among team members. With TypeScript, developers can refactor code with confidence, relying on the compiler to catch inconsistencies and errors. Moreover, as TypeScript continues to evolve, you'll find that learning and utilizing its features will position you well for future developments in programming environments. Whether you're building simple applications or complex systems, TypeScript's structured approach allows you to craft code that is not only functional, but also maintainable and scalable. So, are you ready to dive deeper? Each feature serves a purpose, and understanding them will give you the power to build robust applications that stand the test of time. Let's embrace TypeScript together and elevate our coding capabilities. When developing applications, you frequently design and manage objects. A key aspect of object-oriented programming is the use of design patterns, which provide proven solutions to common problems that developers face. In this lesson, we will explore several core design patterns in TypeScript, helping you build maintainable and scalable applications. So far, we learned about TypeScript, an extension of JavaScript that adds static types, helping developers write cleaner and more reliable code. We explored its core features like basic and complex types, enums, interfaces, and generics, which enhance type safety and maintainability. The latest version, TypeScript 5, introduces improvements such as better enum handling and enhanced decorator support, streamlining the development process. Ultimately, mastering TypeScript equips you for better collaboration and future developments in programming. Now, we will cover core design patterns in TypeScript that will strengthen our understanding of how to effectively manage code. Now let's take a look at how to implement the Singleton pattern in TypeScript with the database connection class. This class is designed to ensure that only one instance is created by making its constructor private, which prevents direct instantiation from outside the class. Instead, the class provides a static method called getInstance. This method checks if an instance already exists. If not, it creates a new instance, establishing a database connection, which is indicated by a console log message. When we call getInstance, we either receive the existing instance or the newly created one, ensuring that all parts of the application utilize the same database connection. This is crucial for resource management, as it avoids unnecessary multiple instances that could lead to inconsistencies and excessive resource consumption. In the usage example, when we call getInstance multiple times, we see that both db1 and db2 refer to the same instance, demonstrating the Singleton pattern's effectiveness in managing object instantiation and promoting a single point of access throughout our application. Now let's see how we can implement the factory pattern in our application to streamline user creation. First, we define an interface called user, which mandates that any user object has a name and role. Next, we create two classes, admin and guest, that implement this interface. Each class has its own specific role. For instance, the admin class assigns the role as admin, and the guest class assigns it as guest, demonstrating how we can create flexible user types. To centralize the user creation process, we then introduce a user factory class. This class contains a static method, createUser, which takes the user type and name as parameters. Inside this method, a switch statement helps us determine which specific user type to instantiate based on the type provided. If the type is invalid, an error is thrown, ensuring that we handle unexpected inputs. Finally, we can see the factory in action with some usage examples, where we create an admin user named Alice and a guest user named Bob. This design allows for easier expansion in the future, as adding new user types won't require modifications to existing client code, showcasing the factory pattern's effectiveness in managing object creation. Now let's implement a simple example of the decorator pattern that modifies the behavior of a notification system. We start by defining the notifier interface, which establishes a common contract for all notification types, requiring a send method that accepts a message. Next, we create concrete implementations of this interface, like email notifier and SMS notifier, which send out notifications in their respective formats. To introduce new functionalities without altering existing classes, we create a base decorator class named Notifier Decorator. This class holds a reference to a notifier instance and delegates the send method to it, allowing us to extend functionality in a flexible manner. Now, let's see how we can enhance the notification's behavior by adding a specific decorator, the logging decorator. This class overrides the send method to incorporate logging functionality, outputting a log message before proceeding to call the send method of the encapsulated notifier. Finally, we put this in action by creating an instance of email notifier, which we then wrap with the logging decorator. When we invoke the send method with a message, we see both the log output and the email notification, demonstrating how the decorator pattern allows us to dynamically add behavior to the notification system without modifying its core functionality. Next, we will explore the observer pattern, which is immensely effective for establishing a publish-subscribe mechanism. In this implementation, we define an observer interface that requires an update method, which will be called when the observed object changes its state. The weather station class acts as the subject by maintaining a list of registered observers and providing methods to add or remove them. Now let's see how we can implement this by adding a setTemperature method to the weather station. When the temperature changes, this method updates the temperature and immediately calls the notifyObservers method. Inside notifyObservers, we traverse through the list of observers, invoking their update methods to notify them of the temperature change. Next, we have the TemperatureDisplay class, which implements the observer interface and receives updates. When an observer is notified, it logs the current temperature to the console in a clean, readable format. This structure allows us to decouple the subject and the observers, enabling easy maintenance and flexibility when adapting to new display types or adding more functionality in the future. Now let's see how we can implement the strategy pattern in a payment processing application. We start by defining an interface called Payment Strategy, which declares a method pay that accepts an amount to be processed. This allows different payment methods to conform to this interface, ensuring that they all implement the payment functionality. Next, we create two concrete classes, Credit Card Payment and PayPal Payment, which implement the payment strategy interface. Each class has its own implementation of the pay method, providing specific behavior for handling payments through credit cards and PayPal, respectively. Now let's take a look at the Shopping Cart class, which takes advantage of the strategy pattern. It has a private property, Payment Strategy, to hold the current payment strategy being used. The setPaymentStrategy method allows us to assign a specific payment strategy implementation at runtime, giving flexibility in choosing the payment method dynamically. Finally, the checkout method invokes the pay method of the selected payment strategy, enabling the shopping cart to process payments seamlessly with different methods. By decoupling the shopping cart from the payment methods, this implementation allows for easy expansion and modification as new payment options become available. Now let's explore the command pattern, which allows us to encapsulate actions as objects, providing a flexible way to handle operations like queuing and undoing actions. In our example, we start by defining a command interface that mandates an execute method. This standardization allows for different concrete command classes to implement their unique behaviors. Next, we introduce the light class, which has two methods, turn on and turn off. These methods represent the actions that our commands will execute. We then create two command classes, light on command and light off command. Each command class holds a reference to a light object and implements the execute method to call the appropriate light action. By separating the command from the action, we enhance flexibility in our system. For instance, the light on command is responsible for turning the light on, while the light off command does so for turning it off. Finally, in the usage section, we instantiate a light object and then create instances of both command classes, allowing us to call their execute methods and see the results. This approach demonstrates the power of the command pattern in organizing and managing operations cleanly and efficiently. By now, we've covered several core design patterns, including Singleton, Factory, Decorator, Observer, Strategy, and Command. Each pattern serves a unique purpose and can significantly improve the structure of your TypeScript applications. Understanding these patterns not only helps in building scalable applications, but also fosters better collaboration among team members as they provide a common language for discussing solutions. As you apply these design patterns in your TypeScript projects, you will find that they enhance code reusability, maintainability, and readability. With a solid grasp of these core concepts, you are better equipped to tackle complex programming challenges and deliver high-quality software solutions. So get out there and start applying these design patterns in your projects. Your code will thank you. In this lesson, we will explore the concept of domain-driven design, DDD, within the context of microservices. DDD is an approach to software development that emphasizes collaboration and a deep understanding of the business domain for which you're crafting the software. By employing DDD principles, you can create applications that are modular, maintainable, and aligned with business needs. So far, we learned about the fundamentals of TypeScript, its features that enhance type safety and maintainability, and core design patterns such as Singleton, Factory, Decorator, Observer, Strategy, and Command. Now we will cover the implementation of domain-driven design in microservices architecture. Domain-driven design encourages developers to deeply understand the business domain they are operating within, allowing them to create a shared language with non-technical stakeholders. This shared language forms the basis for all discussions regarding the system, known as the ubiquitous language. When applied to microservices, each service operates as a bounded context, encapsulating its own domain logic, data models, and rules. A bounded context serves as a boundary within which a particular model is defined and applicable, enabling teams to work independently on different services without causing conflicts. Now let's take a look at how we can define the product management service using TypeScript. We begin by creating an interface, product, which lays out the essential properties of a product, including its ID, name, description, and price. This interface serves as a clear contract, enabling developers to maintain consistent data structures throughout the application. Next, we implement the product service class, which encapsulates all functionalities related to managing products. It contains a private array, products, that holds the product instances. We define two methods within this class: add product, which allows adding new products to the array, and get product, which retrieves a product by its ID. This separation of concerns promotes maintainability and clarity, making it easier for teams to collaborate. After defining these components, we then create an instance of product service and add a sample product to demonstrate functionality. By calling the getProduct method, we can retrieve and log the product details, showcasing the successful integration of our domain model within the product management service. This structured approach not only reinforces type safety, but also simplifies evolving requirements in a microservices architecture. Now let's implement the order management functionality of our e-commerce application. We start by defining an order interface that outlines the structure of an order, including properties such as order ID, product ID, customer ID, and quantity. This design allows us to set clear expectations for the data that an order should contain. Next, we create the order service class, which manages a collection of orders. Inside this class, we employ a private array to hold the order objects, thus encapsulating the order data. The createOrder method allows the addition of new orders to the array, promoting simple order creation. This method takes an order object as an argument and pushes it into the orders array. To retrieve an order, we implement the getOrder method, which takes an order ID as a parameter and utilizes the find method to search for an order with a matching ID within the array. If found, it returns the corresponding order object. If not, it returns undefined. Finally, we demonstrate how to use the order service by creating an instance of it and adding an order. By logging the result, we can visualize the order that was stored, showcasing how this service operates independently while enabling functionality for the broader e-commerce system. Now let's implement a simple event bus that facilitates communication between different services in our e-commerce application. We start by defining an interface called event, which includes the event type and the associated data. This establishes a standard structure for our events. Next, we create the event bus class, which manages listeners for various events. It contains a subscribe method to allow services to register their interest in specific event types by providing a listener function. When an event of a particular type occurs, these listeners will be invoked with the event data. The publish method in the event bus is responsible for broadcasting an event to all subscribed listeners. When we call this method, it looks up the listeners for the specified event type and invokes them with the associated data. To see this in action, we create an instance of event bus and have a service subscribe to an order-created event. When we publish a new order data, it triggers the listener, which logs the relevant order information. This flexibility allows us to implement responsive services while keeping them decoupled, a fundamental principle of microservices architecture. Now let's implement a user interface and a user service class to handle user management in our application. The user interface defines the structure of a user object, requiring an ID, name, and email attribute, ensuring that all user data conforms to this format. This encapsulation enables clear data representation in our application. Next, we will create the user service class, which will manage the user accounts. This class features a private array to hold the users we're managing, promoting encapsulation and preventing direct modification of user data from outside the class. It provides two essential methods: addUser and getUser. The addUser method allows us to add new users to our internal user array, while getUser retrieves a user by their ID, returning either the user object or undefined if no match is found. Now let's see how we can utilize this user service. By creating an instance of user service, we can add a user and then retrieve and log their information. This setup serves as a foundational element in our user management service, adhering to the principles of domain-driven design by encapsulating domain logic within its bounded context. Now let's implement the mechanism for notifying the order service whenever a user updates their email address. we start by subscribing to an event, user email updated, within our event bus. This allows the application to listen for a specific event, and when the event is triggered, it will execute a callback function, logging the user's ID and the new email address. This establishes a clear connection between the change in user information and the auto service's potential need for that updated information. Next, we'll simulate an email update for a user with the ID C001, changing their address to alicenew@example.com. We achieve this by invoking the publish method of our event bus, passing in an event object that specifies the event type and the data containing the user ID and new email. The event bus then notifies any active listeners of this event, resulting in the output that confirms the action, illustrating how our services communicate without direct coupling. By implementing this approach, we ensure that changes within one service can propagate to others, maintaining modularity and enhancing maintainability within our microservices architecture. As you design your services, remember that domain-driven design emphasizes that the domain model should reflect the real-world processes and structures of your business. Crafting effective domain models allows your software to grow and evolve alongside the business it supports. In this case, you can think about your entities, like product, order, and user, as the main components that represent different bounded contexts. These models allow developers and stakeholders to work together to refine the system's behavior to match business goals. One of the ultimate benefits of using DDD is that you create a more cohesive and adaptable software architecture. In a rapidly changing business environment, applications need to be able to shift and pivot quickly. With well-defined bounded contexts and a focus on the domain, you're setting a solid foundation for future growth. In closing, as you embark on applying domain-driven design principles to your microservices architecture, embrace the concept of collaboration across teams. Foster open communication, cherish the shared language, and encourage exploration and experimentation to advance your understanding of the domain. By focusing on these principles, you will build software systems that are not only robust and scalable, but also more aligned with the real needs of the business. This intelligent architecture will ultimately improve productivity and satisfaction among team members and stakeholders alike. Now go ahead, apply what you've learned here, and watch your software projects flourish, reflecting the very essence of the business domain. Until now, we've discussed the fundamental programming constructs of TypeScript, such as interfaces, classes, objects, and enums. So far, we have learned about domain-driven design, DDD, in the context of microservices, emphasizing the importance of a shared language and independent bounded contexts for each service. We explored building a product management service using TypeScript, followed by an auto-processing service, and discussed their interaction through an event-driven architecture. Additionally, we introduced a user management service, demonstrating how changes in user information can affect orders while maintaining loose coupling through events. Lastly, we highlighted the significance of crafting effective domain models to ensure that software architecture aligns with business needs and fosters collaboration among teams. Now we will delve deeper into the core principles of TypeScript, focusing on advanced types and their applications within a TypeScript codebase. Now let's see how we can implement a user profile update function using TypeScript's utility types. In this example, we start by defining an interface called userProfile, which represents the structure of a user with properties like name, email, age, and an optional bio. The goal is to create a function named updateUserProfile that leverages the partial T utility type. This utility allows us to specify that any properties of a user profile can be omitted when calling the function, making them optional. This is particularly useful in real-world applications where a user may not provide all profile details at once. By accepting a partial user profile type as its parameter, our function enables callers to submit any subset of user information without the need to include every single property. Additionally, we demonstrate the function's flexibility with examples of how to call it, showing that we can update just the name or the email and bio, thereby enhancing the user experience when managing profile information. Now let's explore how to create a comprehensive user profile using TypeScript's required T utility type. This utility constructs a new type, complete profile, that enforces all properties of the user profile interface to be required. Even previously optional properties, like age, must now be included whenever a complete profile object is created. Next, we will look at the displayProfile function, which takes a complete profile as an argument and outputs the user's details. This reinforces the importance of including every required property to ensure that all necessary information is provided when displaying the profile. For demonstration, we create a valid profile object that complies with this structure, ensuring that the name, email, and age fields are populated. This design enforces data integrity since any attempt to call displayProfile with a profile missing any of these properties would result in a compile time error, thus prompting developers to always provide complete data. In this way, required T helps maintain strict type safety and enhances the reliability of the application. Now let's see how we can implement a scenario using the pick_t utility type in TypeScript. We begin by defining an interface called userProfile, which encapsulates various properties of a user, such as name, email, password, and age. This interface acts as our blueprint for a complete user object. However, when dealing with user login functionality, we only need a subset of these properties, specifically the email and password. To achieve this selective type extraction, we create a new type called userLogin that utilizes the pick utility type. The pick allows us to define userLogin in a way that it only includes the necessary properties from userProfile. In the login function, we accept an argument of type userLogin, which ensures that only the required fields are passed in when a user tries to log in. As we declare user login details, we populate it with the required fields, facilitating type safety throughout our code. This approach clarifies our intent and reduces the risk of passing unnecessary or incorrect information to the login function, reinforcing good practices in type management. Now let's see how we can implement a user profile type that excludes sensitive information using TypeScript's utility types. In our code, we start by defining an interface called userProfile, which captures essential user details such as name, email, password, and an optional bio. However, sharing this information directly may pose security risks, particularly with sensitive data like passwords and personal bios. To address this, we create a new type, limited user profile, by utilizing the omit utility type, which allows us to construct a version of user profile that excludes specific properties, in this case, the password and bio. This design pattern is particularly useful when we want to send user information without compromising security. We then define a function, sendUserProfile, which accepts a limited user profile parameter, ensuring that only safe data is passed to it. This function logs a message indicating that we're sending user profile information, but without sensitive details. Finally, we instantiate a limited user profile object with a name and email, demonstrating how to use our newly defined type while securely handling user information. Now let's see how we can implement a map type in TypeScript to make properties optional. In the code, we define an interface called user, which consists of 3 required properties: username, password, and email. To create a new type where all these properties are optional, we utilize a map type syntax. The type partialUser is defined using a TypeScript feature that iterates over each property P in the user interface and appends a question mark to indicate that each property does not need to be present when creating an object of this type. Next, we demonstrate this with an instantiation of partialUser named newUser. In this instance, we provide only the username property, while the other properties, password and email, can either be omitted or included later without causing type errors. This flexibility is particularly useful for situations where you might want to create or update user profiles incrementally, allowing you to handle data with varying levels of completeness. Map types greatly enhance the expressiveness of TypeScript, enabling developers to create flexible yet type-safe structures. Next, we will write a conditional type that leverages TypeScript's built-in capabilities to evaluate types at compile time based on specific conditions. In our example, we define a type called checkArray that takes a generic type parameter t and checks if t extends the type of any array. If it does, checkArray resolves to the string literal type array, indicating that t is an array type. Otherwise, it resolves to not an array, confirming that t is not an array. To see this in action, we create 2 test types using checkArray. The first, test1, applies checkArray to number, which is indeed an array type, so test1 becomes array. Conversely, the second test type, test, uses checkArray with a plain string, which is not an array type, resulting in not an array. This demonstrates how conditional types can provide more robust type checking and enhance the type safety of our TypeScript applications by allowing types to adapt based on given inputs. Now let's take a look at how we can achieve stricter type differentiation in TypeScript using branded types. In this example, we define 2 unique symbols, brand1 and brand2, which act as distinctive identifiers for our types. We then create 2 types, branded type and another branded type, both containing a numeric value, but distinguished by their unique brand properties. This approach allows TypeScript to enforce strict type checking against unintentional type assignments. Next, we implement a function, useBrandedType, which accepts a parameter of type branded type. This function simply logs the value property to the console. To illustrate the power of our branded types, we create a valid branded type instance and an invalid another branded type instance. When we attempt to pass the invalid instance to the useBrandedType function, TypeScript raises an error. This highlights how branded types enhance type safety by preventing the accidental mixing of similar structures, thus reducing potential runtime errors during development. This technique is especially useful in larger codebases, where maintaining type integrity is crucial for collaboration and maintainability. Now let's take a look at how we can leverage the keyoff operator to enhance type safety in our TypeScript applications. We start by defining an interface called book, which represents the structure of a book object with three properties: title, author, and pages. The keyoff operator is then utilized to create a new type called bookKeys, which automatically generates a union type of string literal types representing the property names of the book interface. This type is particularly useful for ensuring that only valid keys from the book interface can be accepted in certain functions. For example, we define a function called printBookKey that takes a parameter of type bookKeys. This function logs the property name to the console. When we call printBookKey with a valid key like title, it works seamlessly. However, if we attempt to call it with an invalid key like ISBN, TypeScript will raise a type error. This demonstrates how the keyoff operator enables developers to write more maintainable and type-safe code by restricting function inputs to valid property names. Now let's take a look at how type assertions work in TypeScript. Type assertions provide a way to inform the TypeScript compiler about the type of a variable, allowing you to bypass certain type checks when you are confident about a variable's type. In the provided example, we start by declaring a variable, some value with the type any, which means it can hold any type of value. We've initialized it with a string. Next, we perform a type assertion by using the as keyword to specify that some value should be treated as a string. By doing this, we can access string-specific properties, such as the length property, which gives us the length of the string. Then we print the length to the console. This demonstrates how type assertions can enhance flexibility in our code, allowing developers to leverage the type system without giving up on type safety. However, it's crucial to use assertions judiciously, as an incorrect assumption about the type can lead to potential runtime errors. Always ensure types are accurately asserted to maintain robust type safety throughout your application. As we wrap this up, remember that mastering TypeScript involves understanding both its basic constructs and its advanced features, such as utility types, map types, conditional types, branded types, and more. These principles not only enhance your code's robustness, but also make it more maintainable and scalable. As you progress, keep experimenting with these concepts in your projects, and watch how TypeScript transforms your development. Our journey with TypeScript doesn't stop at fundamental types. Today, we'll explore advanced types and utility types that enhance code robustness and efficiency. So far, we learned the foundational programming constructs of TypeScript, including interfaces, classes, and enums, and we delved into the application of domain-driven design, DDD, in microservices. We've examined the building of various services, such as product management and user management, and their interactions through event-driven architecture. Now, we will cover more advanced TypeScript concepts, such as map types, conditional types, and type assertions that can significantly improve our type manipulation and data integrity in code. Now let's take a look at how we can implement the updateUserProfile function using the partial T utility type. First, we define an interface named userProfile, which includes properties like name, email, and age, along with an optional bio. This structure allows us to represent a comprehensive user profile. Next, we create the updateUserProfile function, which accepts a parameter called profile of type partial user profile. The beauty of using partial here is that it transforms all properties of the user profile interface into optional properties. This means the function can be invoked with just a subset of the user's data, enhancing flexibility in our application. For instance, when we call updateUserProfile with just the name, the function executes without requiring the complete user profile object. Similarly, we can also pass an object containing email and bio, showcasing how partial T allows us to focus on just the fields we want to update. This makes managing user profiles in various scenarios much simpler and more efficient, as we don't have to deal with filling out unneeded properties. Next, we will write the following code that demonstrates the utility type required T. In this example, we begin with an interface called userProfile, which defines three properties: name, email, and age, with age being optional. This structure serves as a foundation for our user profile data, where having a name and email is essential but allows the age to be omitted. Now let's see how we can implement required user profile to enforce that all properties become necessary. we create a complete profile type that ensures every property in user profile is required, thus eliminating the optional nature of the age field. The display profile function is then defined to accept a complete profile type, which means it must receive an object containing all three properties whenever it is called. Finally, the valid profile constant is declared as a complete profile, illustrating how all properties must be provided. This strict typing helps enforce data integrity, promoting reliable code practices by ensuring the absence of missing fields during function calls. This approach not only enhances type safety, but also clarifies the expected structure of our user profile data. Now let's see how we can implement the pict utility type to create a more focused type. In this example, we begin by defining an interface called user profile, which includes various properties such as name, email, password, and age. This comprehensive structure provides a blueprint for user data, but sometimes we only need a subset of this information for specific functionalities, like user login. Next, we create a new type, user login, using the pic utility. This newly defined type includes only the email and password properties from the user profile. By doing this, we streamline our function requirements, allowing the login function to accept only the essential information it needs to proceed with user authentication. This not only reduces the risk of passing unnecessary data, but also enhances type safety by ensuring that only the relevant fields are utilized. Finally, we demonstrate how to use this simplified user login type by creating an object that contains both an email and a password, and subsequently calling the login function with those details. This approach exemplifies the practical use of the pic utility, allowing for efficient data handling in applications while maintaining clarity and precision in type definitions. Now let's see how we can implement the omit utility type in TypeScript to create safer representations of our data. In this code, we define an interface named user profile, which encapsulates user-related information, including sensitive details like password and an optional bio. Here, we want to create a new type, limited user profile, which excludes the password and bio properties to ensure that we don't expose this sensitive information when sharing user data. Next, we define the sendUserProfile function, which takes an argument of type limited user profile. This function is designed to log the user profile while safeguarding sensitive data. By employing omit, we can ensure that when we create a limited user profile, it will only include the name and email fields, effectively excluding any properties that could compromise user privacy. Finally, we see an example of how to instantiate a limited user profile with a name and email, and we pass it to the sendUserProfile function. This approach promotes better security practices by minimizing the risk of unintentionally sharing sensitive data, illustrating the practical benefits of using the omit utility type in our applications. Now let's implement the following setup to illustrate how map types can transform existing types into new variants. Here, we define an interface called user, which has required properties such as username, password, and email. These properties will be crucial when handling user accounts in an application. Next, we're going to create a new type named optional user using map types. By leveraging the map type syntax, we iterate over each key of the user interface. This is achieved by using keyOfUser, which generates a union of all the property names in the user interface. We append a question mark to each property in the iteration to denote that all properties are now optional. This transformation allows us to create user objects where any combination of properties can be included or omitted, thus enhancing flexibility in scenarios like forms or user updates. Finally, we instantiate a variable new user of type optional user, demonstrating that we can provide only the username property while still satisfying the structure defined by our new type. This approach is particularly useful when dealing with dynamic forms or partial updates in applications. Now let's explore conditional types, which allow for powerful type evaluations based on certain conditions. We will write a type called checkArray that uses a conditional to determine if a given type T is an array. This type employs the extends keyword to check if T fits the shape of an array type, returning array if true and not an array otherwise. Next, we create two test types, test1 and test, to see this in action. Test1 applies our checkArray type to number, representing an array of numbers which will evaluate to array. In contrast, test2 checks the type string, which is not an array, thus it will evaluate to not an array. This showcases the strength of conditional types in TypeScript, enabling you to create dynamic and flexible types based on type characteristics. You can build versatile and adaptable code structures, enhancing type safety and facilitating more complex type logic within your applications. Now let's see how we can implement branded types to enhance type safety in our application. We begin by creating two unique symbols, brand1 and brand2, which will serve as distinctive identifiers for our branded types. Next, we define branded type and another branded type, both of which share a similar structural definition featuring a value property. However, they each include a brand property associated with their respective symbols, effectively differentiating them. The function useBrandedType accepts an argument of type brandedType, allowing us to log the value property. Then we create an instance of brandedType called validBrand, ensuring it has the correct symbol brand. To illustrate the type safety that branded types provide, we also create an invalidBrand variable of type another branded type. Attempting to use this in place of branded type would result in a compilation error, preventing potential runtime issues. By doing this, we create an enforced distinction between types that, while structurally similar, represent different concepts and usages in our code, demonstrating the practical advantages of leveraging branded types in TypeScript. Now let's see how we can implement the keyoff operator in TypeScript to enhance code safety. The keyoff operator allows us to extract the property names from a given type, creating a union of those property names as string literal types. In our example, we define an interface called book, which includes properties for title, author, and pages. By applying the keyoff operator to the book interface, we create a new type bookkeys that resolves to a union of its property names, title, author, and pages. Next, we implement the printBookKey function, which takes a parameter of type bookkeys. This function prints a message indicating that the passed key corresponds to a property of the book interface. By using bookkeys as the type for the function parameter, we ensure that only valid property names can be passed, thereby enforcing type safety. For example, calling printBookKeyTitle works fine, but if we attempt to pass a non-existent property like ISBN, TypeScript will throw an error, guiding us to correct our code. This demonstrates how the keyoff operator can be a powerful tool for creating safer and more robust TypeScript applications. Now let's take a look at type assertions, a powerful feature that enables us to inform the TypeScript compiler about the specific type we expect a variable to be. In our example, we start by declaring a variable named SomeValue with the type any, which means it can hold any value. This flexibility can be beneficial, but it also means that TypeScript cannot infer more precise types, potentially leading to runtime errors. Next, we proceed to assert that SomeValue is indeed of type string using the as keyword. This assertion allows us to safely access properties specific to strings, such as length. By doing this, we assign the length of the string stored in SomeValue to the variable strLength. Finally, we log strLength to the console, demonstrating how type assertions enable us to work with potentially ambiguous types while maintaining type safety where it matters. It's crucial, however, to use type assertions wisely, as incorrect assumptions about a variable's type can lead to runtime errors. In this tutorial, we've taken a deeper dive into advanced types and utility types in TypeScript. We've covered various utility types like partial T, required T, pick T, K, and omit T, K, which enrich our applications with more robust type manipulation techniques. We also examined map types, conditional types, branded types, the keyoff operator, and type assertions, each providing unique ways to enhance our code's type safety and maintainability. As you integrate these advanced types into your TypeScript projects, you'll find that they not only improve code clarity, but also help prevent errors early in the development process. Keep experimenting with these concepts in your code, and soon, you'll master the intricate and powerful features that TypeScript has. The Singleton pattern is a creational design pattern that ensures a class has only one instance and provides a global point of access to it. This allows us to manage shared resources and controls access effectively, preventing conflicts and inconsistencies in data during runtime. So far, we learned about design patterns as reusable solutions to common software development challenges, enhancing efficiency and maintainability. We covered foundational constructs in TypeScript, including interfaces and classes, and explored concepts like domain-driven design and utility types. Additionally, we discussed various design patterns such as Singleton, Factory, Observer, Strategy, Adapter, and Command, highlighting their practical applications and benefits in improving code structure. As we move forward, we will continue to deepen our understanding of utilizing design patterns in software development. In this lesson, we will dive into the Singleton pattern, exploring its implementation, variations, and use cases, so that by the end, you'll fully understand how and when to apply it in your projects. Now let's implement the Singleton pattern in TypeScript. We begin by creating the Singleton class with a static property instance that will hold the single instance of the class. the constructor is marked as private, which prevents external classes from creating new instances directly. This enforces the idea that only one instance should exist. Next, we define the static method getInstance, which checks if an instance already exists. If it doesn't, it creates a new instance and assigns it to the static instance property. This ensures that every time getInstance is called, it returns the same instance, enforcing the singleton behavior. Additionally, we've added a method called sayHello, which can be invoked on the singleton instance. This method simply logs a message to the console, demonstrating that you have access to the singleton instance's methods. By following this structure, we've effectively implemented the singleton pattern, providing controlled access to a single instance of the class throughout the application. Now let's take a look at the configuration manager, which exemplifies practical usage of the singleton pattern. This class is designed to manage application settings through a private settings object, preventing multiple instances from existing simultaneously, thus maintaining consistency across the application. To start, we define Configuration Manager with a private static variable instance that holds the single instance of the class. The private constructor is crucial, as it ensures that no external class can create an instance directly. Instead, we provide a static method getInstance, which checks if an instance already exists. If it doesn't, it creates one, ensuring that further calls return the same instance. The set method allows clients to update the configuration settings by providing a key-value pair, while the get method retrieves the value associated with a given key. This design guarantees that access to configuration settings is centralized, making our application scalable and easier to manage without the risk of having conflicting configurations. By using this pattern, we ensure that every part of our application relies on the same source for configuration information. Now let's see how we can implement a thread-safe version of the singleton pattern to avoid issues in multi-threaded environments. The thread-safe singleton class begins with two private static properties: instance, which will hold the singleton instance, and lock, an object used to synchronize access to the instance creation process. Next, we utilize a private constructor to prevent external instantiation of the class. This enforces our singleton logic by controlling how instances are created. The crucial part is the getInstance method, which first checks if an instance already exists. If it doesn't, we enter a synchronized block using our lock object. This ensures that only one thread can access this critical section at a time, thereby preventing race conditions where multiple threads could create separate instances. Inside the synchronized block, we again check if the instance is still absent before creating a new instance of thread-safe singleton. This double-checking pattern is necessary to ensure that even if multiple threads pass the first check at the same time, only one will successfully create the instance. Finally, once the singleton instance is established, the method returns it, guaranteeing that all future calls to getInstance will reference the same instance. Now let's take a look at how to implement a singleton logger class, which ensures that only one instance of the logger exists throughout the application. The class begins with a private static variable, instance, which will hold the single logger instance. The constructor is marked as private to prevent external instantiation, enforcing the singleton pattern's principle. Next, we implement the getInstance method, which serves as the access point for obtaining the logger instance. This method checks if an instance of logger already exists. If not, it creates a new instance and assigns it to instance. This ensures that every call to getInstance returns the same instance, thereby maintaining a consistent logging service across the application. Once our logger class is established, we can utilize it for logging messages. By calling logger_getInstance, we can create logger1, which is the first access to our logger. When logger1 logs a message, it utilizes the log method, which formats the message with a prefix and outputs it to the console. Similarly, when we create logger2 by calling getInstance again, we find that it references the same logger instance as logger1, confirming the correctness of our implementation. This guarantees that all log messages are effectively managed through a singular logging service. While there are clear advantages to using the singleton pattern, it's essential also to be wary of potential downsides. Because the singleton controls instance creation, it could lead to tight coupling in your code. This tightly coupled design can make it hard to modify or replace the singleton later on. For instance, if you wanted to enhance the logger behavior or replace it with a different implementation, you might find it involved multiple refactors. To mitigate this risk, you can consider using dependency injection, DI. By injecting dependencies when needed rather than relying directly on the singleton, you can keep your code loosely coupled. This way, you can easily swap out implementations in tests without changing your core logic. Now let's implement the application class, which utilizes dependency injection alongside the singleton pattern for enhanced flexibility. This class requires a logger instance to function effectively, allowing us to pass any logger implementation at instantiation. In the constructor, we accept a logger parameter of type logger, which is stored in a private property. This allows the application to log messages without being tightly coupled to a specific logger instance. By maintaining this separation, we gain the ability to replace or mock the logger in our tests, enhancing the testability of our code. Next, we define the run method within the application class. When this method is called, it logs a message indicating that the application is starting. The logging action exemplifies how the logger's functionality is smoothly integrated into the application's workflow without directly invoking any static methods or creating a singleton instance inside the application class itself. In our setup code, we obtain an instance of the logger using loggerGetInstance, reinforcing the singleton nature. We then create a new instance of application, passing in the logger instance, and call its run method, demonstrating the cohesive interaction between the application and logger components. To wrap up, the singleton pattern is everywhere in programming, from operating systems managing resources to frameworks that require a unified configuration approach. Its simple implementation makes it accessible, but its implications need careful consideration. Understanding when to use it and how to avoid pitfalls such as tight coupling or threading issues is essential for creating robust applications. In this lesson, we've covered what the singleton pattern is, how to implement it with TypeScript, its use cases, and the importance of balancing flexibility with the principles of the pattern. As you dive into your projects, keep this powerful tool in your toolkit and consider the role it could play in your architecture. Thank you for joining me in exploring the singleton pattern. Make sure to practice implementing it in your applications and consider how it could fit with other patterns we've discussed. The next creational design pattern we'll study is the prototype pattern. This pattern is fascinating because it allows the creation of new objects by copying or cloning existing ones, rather than instantiating new ones from scratch. This could lead to improved performance and flexibility, especially when object creation is expensive. So far, we learned about the singleton pattern, a creational design pattern that restricts a class to a single instance, ensuring a global point of access. We explored its implementation in TypeScript, looking at practical applications like configuration management and logging services, while also addressing potential issues in multi-threaded environments. Additionally, we discussed the importance of reducing tight coupling through dependency injection to maintain flexibility in code. As we continue, we will cover the essentials of the prototype pattern, its advantages, and scenarios where you might want to implement it in your projects. Now let's see how we can implement the prototype pattern in TypeScript with a clear structure for our prototypes. We begin by defining a prototype interface that mandates the implementation of a clone method, which any concrete class must fulfill. This method will be responsible for returning a copy of the object that implements the interface. Next, we will create a concrete prototype class that adheres to this interface. This class introduces a private field called state, which will hold specific data for each instance. The constructor initializes this state, allowing each concrete prototype instance to maintain its unique information. The real magic happens in the clone method, where we return a new instance of concrete prototype using the current state. This effectively produces a duplicate of the original object, showcasing the efficiency of cloning over instantiation. Additionally, we include a getState method to retrieve the state value, making it easier to inspect the cloned objects. Through this design, we establish a solid foundation for implementing the prototype pattern, simplifying object creation while promoting code reusability and efficiency. Now let's implement the following classes to illustrate the prototype pattern with graphical shapes. We begin by defining an abstract class called shape, which implements the prototype interface. The core purpose of this abstract class is to establish a contract for its subclasses. It mandates that any shape must implement a clone method that returns a new instance of the same type. Next, we create the circle class that extends shape. This class takes a radius as a parameter upon initialization and overrides the clone method. By invoking newCircle, this radius, within the clone method, each cloned circle retains the original's radius, allowing us to create variations easily without incurring the overhead of reinitialization. Similarly, we define the square class, which also extends shape. It encapsulates a side length and implements the clone method in the same manner, ensuring that a cloned square has the same dimensions as the original. This design encourages efficient duplication of shapes, fulfilling the objectives of the prototype pattern by enabling the creation of distinct instances while leveraging shared properties. Now let's see how we can implement the functionality of our shapes using the prototype pattern in practice. We begin by creating an instance of a circle with a radius of 10, which represents our original shape. By calling the clone method on this instance, we generate a new shape that is an exact copy of the original, allowing us to work with it independently. We can verify that both the original and cloned circles have the same radius by logging their values to the console, demonstrating how the properties are retained during cloning. Next, we create an instance of square, initializing it with a side length of 5. Similar to the circle, we call the clone method to produce a cloned square. Again, we log the properties of both the original and cloned squares, confirming that they share the same dimensions. This exemplifies the effectiveness of the prototype pattern, enabling us to create variations of shapes efficiently without the need for repeated instantiation. Students should note how easy it is to manage and manipulate cloned objects, thereby enhancing flexibility in our drawing application. Now let's see how we can implement a user class that leverages the prototype pattern for efficient cloning. In this example, the user class implements the prototype interface, indicating that it has a clone method designed to create copies of user instances. The constructor takes name and permissions as parameters, which are properties of each user. Next, we'll take a closer look at the clone method, which plays a crucial role in maintaining object integrity during the copying process. By using the spread operator, we ensure that the permissions array is deeply copied. This means that when a user is cloned, any modifications to the permissions of one instance won't inadvertently impact another. This is vital in scenarios where users may have differing permission settings that must remain independent. Additionally, we have getter methods such as getName and getPermissions, which allow us to access the user's name and permissions without directly exposing the properties themselves. This encapsulation promotes better object-oriented practices by protecting the internal state of the user objects. Overall, this implementation illustrates not just cloning, but also good design principles in action. As we explore further, it's essential to consider when to use the prototype pattern. It can be particularly advantageous in scenarios where object creation is relatively expensive, such as when interacting with external resources, initializing complex configurations, or performing heavy computations during object setup. If you find yourself frequently creating similar objects or requiring variations, the prototype pattern can streamline your process. Consider also the implications of using this pattern in conjunction with other design patterns. It can synergize well with the factory method pattern. The factory method creates objects based on certain conditions. If you can produce a prototype of that object, the factory can significantly enhance its effectiveness. Now let's implement the following widget class, which exemplifies the prototype pattern in our application. This class holds two properties, an ID and a name, which are crucial for identifying and managing the widgets. To facilitate cloning, we implement a clone method that creates new instances of widget. Within this method, we utilize a unique widgeted counter that ensures every cloned widget receives a distinct ID. This is particularly important because widgets might serve specific roles within the application where uniqueness is necessary. Think about managing multiple UI components that share a similar base but should not have identical identifiers. Additionally, we include a getName method, allowing access to the widget's name for display or processing within the application. The design encourages efficient creation of UI components as it copies existing configurations rather than rebuilding from scratch, thus optimizing both performance and maintainability. Each time a widget is cloned, the counter increments automatically, emphasizing thoughtful management of unique identifiers in our cloning strategy. Finally, as we wrap up our exploration of the prototype pattern, let's reflect on its versatility. This pattern allows developers to encapsulate complex object creation logic, enhances performance through cloning, and fosters a flexible architecture. By using prototypes, you afford yourself better control over how objects are constructed and maintained throughout your applications. In conclusion, the prototype pattern is a powerful tool for creating instances painlessly while minimizing overhead. It helps to create a flexible codebase and relies on the shared state of objects to maintain efficiency. As you delve into your projects, keep the prototype pattern in your toolkit, ready to tackle those situations where cloning offers a clear advantage. Thank you for joining me on this journey into the prototype pattern. Let's continue coding smartly and now let's take a look at how we can implement the character and character builder classes to demonstrate the builder pattern in TypeScript. The character class is designed to encapsulate several properties, such as name, health, strength, and armor, which are provided through a character builder instance. This aggregation allows us to sidestep the potential confusion of having numerous constructor parameters, especially when creating complex objects. The character builder class initializes with a mandatory name and sets default values for health, strength, and armor. It provides chainable setter methods such as setHealth, setStrength, and setArmor, allowing you to customize your character step by step. These methods return the builder itself, enabling a fluent interface where multiple properties can be modified without cluttering the code. Once you're ready with your configurations, the build method instantiates a new character, passing itself to the constructor. This encapsulation promotes a readable and maintainable approach to object creation while ensuring proper management of the character's attributes. Overall, this implementation highlights how the builder pattern enhances clarity and flexibility in object construction by allowing you to define complex objects through an intuitive and streamlined process. Let's explore an example that showcases how the Character Builder class aids in building a character for our game. By initializing a new instance of Character Builder and assigning a name, we establish the base attributes for the character. The builder's methods, setHealth, setStrength, and setArmor, enable us to tailor these characteristics incrementally. Each method returns the builder itself, allowing for method chaining that simplifies the code flow. After configuring the desired attributes, we invoke the build method, which constructs and returns a character class instance based on the settings defined in the builder. Once the character is built, calling the describeCharacter method on the resulting object provides a brief overview of the character's attributes. This method not only improves readability, but also reduces the likelihood of errors that can occur with a constructor that accepts numerous parameters. In summary, this example effectively demonstrates the builder pattern, highlighting its benefits in promoting both clarity and efficiency in the process of object creation. Now let's take a look at the implementation of the Pizza and Pizza Builder classes using the builder pattern. In this setup, the Pizza class is designed to hold the characteristics of a pizza, namely its size, toppings, and crust type, which are all defined in the constructor that accepts a Pizza Builder instance. This approach keeps the pizza's construction logic contained within the builder, promoting clear separation between object construction and its representation. The Pizza Builder class initializes with a size parameter and has methods for adding toppings and setting the crust type. Each method in the builder returns this, which allows for method chaining and enhances the fluidity of constructing a pizza. This means you can easily build complex pizza orders step by step without overwhelming the user with an extensive constructor. Finally, the build method in the Pizza Builder class creates an instance of pizza using the properties that have been defined. By following this pattern, we ensure that we're creating pizzas in a clean and manageable way, minimizing the risk of errors while allowing for maximum flexibility in customization. Let's explore the implementation of a pizza order system utilizing the builder pattern. We start by creating a pizza class that encapsulates essential attributes of a pizza, such as size, crust type, and toppings. In its constructor, the class accepts a pizza builder, ensuring that all characteristics are defined according to the builder's guidelines. Following this, we establish the Pizza Builder class, which sets up the necessary attributes for the pizza. The builder begins with a designated size and provides methods like addTopping for adding toppings and setCrust for determining the crust type. Each of these methods returns the builder itself, enabling a fluid, chainable interface that significantly enhances both readability and usability. Finally, let's demonstrate how to create a specific pizza using our builder. We create a new pizza builder, designate it as large, select a thin crust, and add 3 toppings: mushrooms, pepperoni, and olives. After that, we invoke the build method to generate the pizza object. This object can then be described with the describePizza method, giving a clear and concise summary of our tasty creation. This example highlights how the builder pattern streamlines the construction of complex objects in a straightforward manner. Now let's implement the house class using the builder pattern, which allows us to construct house objects with varying configurations without cluttering the constructor. Our house class includes essential properties like the number of rooms, the presence of a garden, and a garage, all set through the house builder. The constructor of house accepts an instance of house builder, ensuring that each property is initialized correctly and neatly. Next, we will write the house builder class, which begins with a specified number of rooms while providing the option to add a garden or garage through chainable methods. The default values for the garden and garage are set to false, promoting a flexible approach to house construction. Each method modifies the state of the builder and returns the builder itself, allowing for a fluent interface that simplifies object creation. Finally, the build method is crucial as it constructs a new house object using the builder's current settings. Now let's see how we can create an instance of a house. By utilizing the house builder, we can easily specify the number of rooms and add amenities like a garden and garage seamlessly, resulting in a concise and clear object creation process. We begin by creating a house builder class that sets the number of rooms and includes default values for features like a garden and garage, which are both initially set to false. This design simplifies the management of these attributes without complicating the constructor. We then add methods such as addGarden and addGarage, which allow us to update the state of the house builder instance by including additional features. These methods return the builder instance itself, facilitating a smooth method chaining process for step-by-step house construction. After configuring the house with the desired features, we finalize the construction by invoking the build method. This method creates a new house instance based on the builder's current state. This approach significantly improves code readability and maintainability, enabling the clear and systematic construction of complex objects like houses. To test our builder, we can succinctly create a house with 3 rooms, a garden, and a garage. The output confirms that the house possesses the specified features, showcasing how effectively the builder pattern manages object construction. Before we wrap up, let's look at a few benefits and considerations when using the builder pattern. One major benefit is that you can construct an object step by step, allowing you to create variations easily by chaining methods to change only what's necessary. This clear interface keeps your code structured and readable. Another advantage is that it allows for immutable configurations after the object is built, supporting better coding practices. Since you're constructing the object with fluent methods, there's less risk of mutating state unexpectedly, which can lead to hard-to-track bugs. However, one downside might be the extra complexity brought about by having additional classes. This complexity can sometimes be overkill, especially when dealing with simple objects. You need to gauge whether your particular scenario merits using the builder pattern or if a straightforward constructor can do the job. In conclusion, the builder pattern is a vital design principle for efficient object creation in complex systems. It helps break down the construction process into manageable and understandable steps, ensuring clarity and maintainability in your codebase. By implementing this pattern, you harness the ability to create multiple representations of an object with ease and precision. Thank you for joining me on this journey through the builder pattern. I hope you feel more equipped to tackle object construction challenges in your TypeScript application. Structural design patterns are powerful tools in a developer's arsenal that offer elegant solutions for organizing objects and classes in larger, more complex systems. These patterns focus on how objects are composed to form larger structures while keeping these structures flexible and efficient. In TypeScript, implementing these patterns becomes even more robust thanks to its enhanced type system and advanced language features. So far, we learned about the builder pattern, which aids in the step-by-step construction of complex objects, enhancing code clarity and maintainability. We explored the implementation of a character builder for creating characters, along with a pizza builder for customizing pizzas. The pattern promotes a clean interface for object creation, supporting variations and ensuring configurations remain immutable. Ultimately, the builder pattern is essential for managing complexity in object-oriented programming, especially in larger applications. Now, we will explore the world of structural design patterns and how they can be a game changer in your TypeScript projects. Now let's see how we can implement the adapter pattern to enable compatibility between a legacy system and a new API. In this example, we start by defining an interface, legacy service, which outlines the method getValue to be implemented by any legacy service. Here, we create an old service class that conforms to this interface and simply returns the number 42, representing the logic from the legacy application. Next, we introduce a new interface called newService, which includes a method fetchValue. The external API service class implements this interface and provides new logic by returning a message string indicating the answer is 42. However, since these two systems operate on different interfaces, we need a way to bridge this gap. This is where the legacy service adapter comes into play. By implementing newService, this adapter takes an instance of legacy service in its constructor and uses it to call getValue within its own fetchValue method. Essentially, this allows clients to call fetchValue on the adapter while internally converting the call to the legacy method. When we create an instance of the adapter with an old service and call fetchValue, we see how seamlessly it integrates the old and new systems, returning the output. The answer is 42. Now let's see how we can implement the decorator pattern in TypeScript to enhance our notification system. We begin by defining a notifier interface, which mandates a send method for sending messages. The basic notifier class implements this interface, providing the simplest form of notification by printing messages to the console. Next, we create an abstract class called Notifier Decorator, which also implements the notifier interface, but is designed to wrap around existing notifier objects. This class holds a reference to a notifier, allowing us to build upon its functionalities while adhering to the core principle of the pattern to extend behavior dynamically. Here we have two concrete decorators, Email Notifier and SMS Notifier, each extending the Notifier Decorator. These decorators enhance the basic notifier by adding their respective notification methods while still calling the original send method. Finally, we instantiate a basic notifier and wrap it with both the email notifier and SMS notifier. When we invoke send on the combined notifier, we see that it first sends the message through the basic notifier, then adds the specialized notifications seamlessly, showcasing how decorators can provide enhanced functionality without modifying the existing codebase. Now let's see how we can implement the facade pattern using a home theater system as an example. In this design, we define two separate classes, audio system and video system. Each class provides basic functionalities to turn on and off the respective system, encapsulating their individual behaviors. This separation allows for modular design, where each system can function independently. Next, we create a home theater facade class that composes these two systems. The facade acts as an intermediary, exposing simplified methods like watch movie and end movie. When the client calls watch movie, the facade automatically turns on both the audio and video systems and indicates that the movie is starting, abstracting away the complexity of handling each system separately. Similarly, the end movie method cleanly shuts them down. By using a facade, we shield clients from the intricate details of subsystem interactions, making our codebase easier to maintain and more intuitive to use. This pattern exemplifies how structural design patterns can streamline interactions in complex systems, leading to cleaner and more understandable code. Now let's take a look at the composite pattern in action, which enables us to work with tree structures for representing part-whole hierarchies. In our example, we start by defining an interface called FileSystemComponent, which declares a method display that both individual files and directories will implement, allowing them to be treated uniformly. Next, we create a file class that implements the FileSystemComponent interface. This class contains a private property for the file name and a constructor to initialize it. The display method returns a string representation of the file, demonstrating how the file system presents its contents. We then define a directory class, also implementing the same interface. This class holds an array of FileSystemComponent objects, allowing it to store both files and other directories. The add method enables adding new components to the directory, and the display method constructs a string that lists all components it contains. Finally, we instantiate a root directory and populate it with files and subdirectories. This structure showcases how we can easily display the contents of the entire file system using our design classes, emphasizing the flexibility and extensibility the composite pattern provides in handling complex hierarchies. Next, we will write the following code to implement the proxy pattern, which enables us to create an interface for another object, acting as a placeholder or surrogate. In this implementation, we define an interface called image, which declares a display method. Then we introduce the realImage class, which implements this interface and is responsible for handling the actual image operations. A key feature of realImage is its constructor, which loads the image from disk immediately upon instantiation, demonstrating the eagerness of resource loading. Now let's look at the proxyImage class, which also implements the image interface, but manages the creation and access to the realImage instance. This class employs a lazy initialization approach. It skips loading the real image until the display method is invoked for the first time. This strategy optimizes resource usage, particularly beneficial when managing large image files. When we create an instance of proxyImage and call its display method, it first checks whether the real image exists. If not, it initializes realImage before displaying the image. Subsequent calls to this method will simply display the already loaded image, showcasing the efficiency gained through the proxy pattern. Now let's take a look at how the bridge pattern facilitates flexibility in a drawing application by decoupling shapes from their colors. We start with an interface named color, which mandates the implementation of the applyColor method, ensuring that any color will have its unique way of expressing itself. Next, we create specific color classes, red and blue, each implementing the color interface. By defining the applyColor method, these classes specify how to apply their respective colors, encapsulating color-related behavior. Moving on, we define an abstract class, shape, which contains a protected property for the color object. In the constructor, a shape can receive a color instance. establishing a relationship between the shape and its color. This design allows us to extend the system easily by adding new shapes or colors without modifying existing classes. We implement concrete shapes, circle and rectangle, that extend shape and implement their own draw methods. When a shape is drawn, it uses its associated color to determine how to paint itself. Finally, we instantiate a red circle and a blue rectangle, showcasing how both the shape and color can evolve independently, demonstrating the power and flexibility of the bridge pattern in object-oriented design. In conclusion, structural design patterns are fundamental in building scalable and maintainable systems. They focus on how objects collaborate, leading to code that not only meets specifications, but also adapts to changing requirements swiftly. By understanding the adapter, decorator, facade, composite, proxy, and bridge patterns, you are well on your way to mastering TypeScript design patterns and enhancing your software design skills. As we wrap up this lesson, remember that implementing these patterns isn't just about writing more code. It's about leveraging efficiency in collaboration and communication within large systems. So, practice these design principles in your projects and watch your application's architecture evolve. Thanks for tuning in and we'll dive into the fascinating world of design patterns, starting with the adapter pattern. This pattern is instrumental in making different classes work seamlessly together, even when they weren't designed to communicate. By implementing a common interface, adapter patterns create a bridge between incompatible systems, making our programs more flexible and manageable. So far, we learned about structural design patterns that help in composing objects into larger systems, maintaining flexibility and efficiency. We discussed various patterns, including the adapter for making incompatible interfaces work, the decorator for dynamically adding responsibilities, and the facade for simplifying complex subsystems. Additionally, we covered the composite pattern for part-hole hierarchies, the proxy pattern for lazy initialization and control, and the bridge pattern for decoupling abstraction from implementation. Now we will cover the adapter pattern in detail, focusing on its implementation and benefits. Now let's implement the adapter pattern with a practical example that bridges the gap between a legacy system and a new interface. We start by defining a temperature fetcher interface that requires a getTemperature method, ensuring consistent behavior across different temperature sources. Our legacy system, represented by the Fahrenheit thermometer, provides temperature readings in Fahrenheit. It implements the temperature fetcher interface and returns a fixed Fahrenheit temperature value. Next, we create the Celsius adapter, which also implements the temperature fetcher interface, allowing it to be used interchangeably with other temperature fetching classes. The adapter takes an instance of Fahrenheit thermometer and converts the Fahrenheit temperature to Celsius by applying the conversion formula. This allows the new system to operate with the legacy thermometer seamlessly. Finally, we instantiate the Fahrenheit thermometer and pass it to the Celsius adapter, allowing us to fetch and log the temperature in Celsius using getTemperature. This elegant arrangement showcases how the adapter pattern enables interaction between systems with incompatible interfaces, illustrating its utility in modern software development while minimizing refactoring efforts. Now let's implement the following code to introduce a new type of thermometer that measures temperature in Kelvin and adapt it to our existing system. We start by creating the Kelvin thermometer class, which includes a method getTemperature that returns a hard-coded temperature value in Kelvin. This thermometer operates independently, but does not conform to the temperature fetcher interface, which our existing code utilizes. Next, we create the Kelvin adapter class that implements the temperature fetcher interface. This adapter takes an instance of Kelvin thermometer as a constructor parameter. Inside the getTemperature method of the adapter, we call the getTemperature method of the Kelvin thermometer, obtaining the temperature in Kelvin. However, we need the reading in Celsius, so we subtract 273.15 from the Kelvin value to convert it. Finally, we instantiate our Kelvin thermometer and pass it to the Kelvin adapter. When we call getTemperature on the adapter and log the result, it gives us the temperature in Celsius, demonstrating how easily we can extend our system's capabilities without modifying existing code. This showcases the adapter pattern's key strengths in promoting flexibility and reusability. Now let's take a look at a practical implementation of the class adapter pattern using a microwave as an example. In this code, we first define the microwave class, which has a method getTime that returns a string indicating the remaining cooking time. This represents our existing class that has a specific functionality. Next, we create the microwave adapter class that extends microwave and implements the temperature fetcher interface. This adaptation allows the microwave adapter to add a new method, getTemperature, which provides a mock temperature reading. By extending the microwave class, we seamlessly integrate additional functionality without modifying the original class. Finally, we instantiate the microwave adapter and utilize both methods. The call to getTime retrieves the cooking time, while getTemperature returns a predefined temperature. This demonstrates how the class adapter pattern enables us to enhance existing functionality, allowing different capabilities to coexist through inheritance, thus making our code more flexible and maintaining a clear separation of concerns. It's important to address when to effectively use the adapter pattern. There are a few key scenarios that signal its necessity. If you have to use an existing class that provides functionality but has incompatible interfaces, that's a perfect candidate for the adapter pattern. Another scenario is when you want to create a reusable class that collaborates with classes from other libraries. Finally, if you find yourself needing to introduce changes to an external component without altering its source code, adapting can help. Let's consider how the adapter pattern compares to other patterns. While similar to the decorator pattern in its structural adaptations, the adapter focuses more on providing compatibility between incompatible interfaces rather than enhancing their functionalities. This clarity helps developers leverage these patterns according to their specific needs without mixing them up. As we delve deeper into the adapter pattern, we can also highlight the common pitfalls. A possible downside is that applying this pattern can lead to complex hierarchies if overused. The more adapters you create, the more convoluted your architecture may become. It's vital to keep the design as straightforward as possible while leveraging the advantages of adaptability. Additionally, ensure that the adapter pattern is genuinely necessary. Sometimes, a simple refactoring can achieve the same results without introducing additional layers of abstraction. Ultimately, the adapter pattern provides significant benefits that lead to a more flexible and maintainable codebase. By allowing incompatible classes to work together through a common interface, you can adapt to evolving requirements our systems face daily. Now let's implement the following code to demonstrate how the adapter pattern can streamline payment processing with different providers. We start by defining an interface called Payment Processor, which mandates a method named Process for handling payment transactions. Next, we create two classes, PayPal and Stripe, that encapsulate their own unique methods for processing payments. The PayPal class features a make payment function, while the Stripe class provides a charge method. These classes serve as our payment providers, but do not conform to a unified interface. To bridge this gap, we develop the PayPal adapter and Stripe adapter classes. Both adapters implement the payment processor interface, allowing them to serve as intermediaries that adapt the specific methods of their respective classes into the common process method. In doing so, they ensure that clients can interact with both payment systems through a consistent API. Finally, we instantiate PayPal adapter and Stripe adapter using the relevant provider instances. This allows us to call process on the adapters seamlessly, demonstrating how the adapter pattern simplifies integration across disparate systems while maintaining clarity and efficiency in our codebase. In conclusion, the adapter pattern is a crucial structural design pattern that enhances the interchangeability of components and allows disparate systems to work together harmoniously. Its role in bridging incompatible interfaces simplifies complex integrations, making our software architecture more robust and flexible. By understanding how to implement this pattern in TypeScript and recognizing its applications in real-world scenarios, you can empower yourself to write highly adaptable and maintainable code. Remember, when you think of integration challenges, the adapter pattern is your ally in ensuring smooth interactions across different systems, making developers' lives a bit easier as we all navigate the complexities of software development. So go ahead and embrace the power of adaptation in your next TypeScript project and see how it transforms your approach to coding. So far, we covered the adapter pattern, which allows for seamless interaction between incompatible systems by acting as a bridge. We explored its implementation through examples involving temperature conversions and payment processing systems, highlighting its role in software flexibility and maintainability. The key components of the pattern include the target interface, adaptee, and adapter, emphasizing a clean separation of concerns. We also discussed some common pitfalls and real-world applications to illustrate its importance in modern software development. Now we will talk about how design patterns, including the adapter pattern, help structure your code in a scalable and maintainable way. Design patterns are solutions to common problems in software design, providing tried-and-true methods that can help developers communicate more effectively and create more robust applications. In essence, they are like toolkits filled with best practices that can be employed to solve specific coding challenges. The significance of these design patterns cannot be overstated. They simplify complex design issues, making them easier to understand and implement. Now let's take a look at how we can implement a simple yet effective example of the repository pattern in TypeScript. We begin by defining a product interface that encapsulates the essential properties of a product, such as ID, name, and price. This establishes a clear contract for what a product should entail within our application. Next, we introduce the product repository interface, which outlines a single method, getProducts, intended to retrieve an array of product instances. By using an interface, we can promote flexibility in our code, allowing different implementations of the repository to be created in the future without altering the code that relies on this interface. Now let's implement the Product API class, which serves as our concrete data source adhering to the product repository interface. It maintains a private array of products and provides the functionality to return this array via the getProducts method. This encapsulation ensures that any modifications to the product data can be handled internally without affecting other parts of the application. Finally, we construct the product service class, which depends on the product repository, allowing it to fetch product data while remaining unaware of the underlying data source. This design enables clean separation of concerns, making it easier to adapt to different data sources such as databases or other APIs in the future. By invoking the displayProducts method, we can effectively present our product information to the console, demonstrating a clear and maintainable architecture. Next, we will explore the implementation of the strategy pattern through a practical example that adheres to the open-closed principle. In this code, we start by defining a discount strategy interface, which serves as a contract for implementing various discount strategies. Following this, we create two concrete classes, NoDiscount and Seasonal Discount. The NoDiscount class simply returns the original amount, while the Seasonal Discount class applies a 10% discount on the given amount, showcasing how different strategies can modify behavior without altering the core logic of the system. Now let's take a look at the shopping cart class. This class has a dependency on the discount strategy, which it receives through its constructor. This design allows us to achieve flexibility. By calling the calculateTotal method, the shopping cart can dynamically apply the specified discount strategy to the amount. This separation promotes adherence to the open-closed principle, as we can easily add new discount strategies in the future without changing any existing code. Lastly, we create an instance of shopping cart that uses the seasonal discount strategy and log the total after applying the discount, demonstrating how easy it is to extend functionality through this pattern. Now let's take a look at how we can implement the observer pattern to adhere to the single responsibility principle. We start by defining an observer interface that mandates the implementation of an update method, which will be called whenever there is a change to the observable subject. Next, we create a concrete class, Product Observer, that implements this interface. Its update method will log the updated product name to the console whenever a notification is received. This separation ensures that the observer's responsibility is solely focused on displaying updates without being entangled with the logic of the product itself. The product class serves as our subject that maintains a list of observers. It contains methods for adding observers and changing its name. Upon changing the name, the changeName method not only updates the state, but also invokes the notifyObservers method. This method iterates over the registered observers and calls their update method, effectively notifying them of the state change. This structure exemplifies the single responsibility principle by ensuring that each class has one reason to change. The product manages its state, while the product observer manages the display, enhancing both maintainability and clarity within our code. Now let's see how we can implement the template method pattern to effectively process user data. We start with an abstract class called UserDataProcessor, which provides a predefined structure for processing data through its process method. This method calls two abstract methods, validate and sanitize. By defining these methods as abstract, we allow subclasses to provide their specific implementations for how data should be validated and sanitized, thereby promoting code reusability. Next, we create a concrete class named defaultUserDataProcessor that extends UserDataProcessor. In this class, we define the validate method, which checks if the input data is empty and throws an error if it is. This ensures that we only work with non-empty data. The sanitize method is also implemented to clean the input data by trimming whitespace and converting it to lowercase, ensuring uniformity in the data format. Finally, we instantiate defaultUserDataProcessor and call the process method with sample user data. This demonstrates how the template method pattern allows us to maintain a consistent processing workflow while permitting customization in the way individual steps are handled, thus enhancing both code readability and reusability. As we bring our discussion to a close, let's revisit the fundamental aspects of design patterns and their implications on code structure. By implementing these patterns, developers can design systems that are not only scalable, but also easier to test and maintain. From encapsulation and the open-closed principle to the single responsibility principle and the template method pattern, the way you structure your code can make all the difference in the long run. Finally, it's crucial to choose the right design pattern that aligns with your application's requirements. Not every problem fits neatly into a specific pattern, so understanding the principles behind these patterns will empower you to adapt your solutions effectively. Always be on the lookout for opportunities to apply these concepts to your projects, as it will ultimately lead to cleaner code and a better foundation upon which to build. The adapter pattern, along with the other design patterns we discussed, serves as a testament to the idea that good software design is more than just writing code. It's about crafting an architecture that stands the test of time. So, as you continue your journey in software development, remember the power of design patterns in structuring your code in a nice, abstract way with scalability in mind. Behavioral design patterns are crucial in software development as they define how objects communicate and interact with one another. They focus on the delegation of responsibilities and the management of relationships among various components in a system. Today, we will delve into the fundamentals of behavioral design patterns, exploring their importance, common types, and practical applications in TypeScript. So far, we have covered the adapter pattern, which enables integration between incompatible systems by acting as a bridge. We also touched on the importance of design patterns for maintaining scalable and maintainable code, discussing principles such as encapsulation, the open-closed principle, and the single responsibility principle. Various patterns, including the repository, strategy, observer, and template method, were explored to highlight their roles in enhancing code flexibility, reusability, and clarity. Now, we will focus on behavioral design patterns and how they facilitate communication between objects and manage responsibilities effectively. Now let's take a look at the implementation of the observer pattern in a weather application. We start by defining an observer interface with an update method that any observer class must implement. This ensures that all observers can respond when they receive new data. Next, we create the weather station class, which serves as the subject. This class maintains a private array of observers and the current weather data. It features methods to add or remove observers from the list, ensuring easy management of subscription. The key method, notify observers, iterates through the list of observers and calls their update methods, passing the latest weather data. When we set new weather data via the setWeatherData method, it automatically triggers a notification to all registered observers. Now we will implement specific observers, such as temperature display and humidity display, which adhere to the observer interface. Each of these classes will log their respective updates to the console whenever the weather data changes. Through this approach, we achieve a loosely coupled architecture, enabling us to easily add or modify observers without affecting the weather station. Now let's implement the strategy pattern for our payment processing system. We begin by defining a payment strategy interface that declares a method for making payments. This sets a clear contract that all payment methods must follow. Next, we create concrete classes for each payment type: credit card payment, PayPal payment, and bank transfer payment. Each of these classes implements the pay method, providing specific logic for processing payments through their respective channels. Next, we introduce the payment context class, which serves as the context where different payment strategies can be applied. It holds a reference to a payment strategy and allows switching strategies at runtime through the setStrategy method. This means users can easily change the payment method without modifying the payment logic, enhancing flexibility. To demonstrate its use, we create an instance of payment context and set it to use credit card payment for a transaction. We then switch to PayPal payment for a different amount. This approach allows you to scale your payment system and easily incorporate new payment methods in the future, adhering to the principles of maintainable and flexible design. Next, we will implement the command pattern to create a simple text editor that allows for writing and undoing actions. The heart of our implementation is the command interface, which defines the essential methods execute and undo, establishing a contract for command objects. The text editor class represents our editing environment, storing the current text and providing methods to write and undo text changes. We then create the write command class, which implements the command interface. This class captures the action of writing to the editor by holding a reference to the text editor instance and the text string to be added. When the execute method is called, it writes the text to the editor, while the undo method reverts the lost written action by removing the text. To manage these commands, we introduce the command manager, which maintains a stack of executed commands. This class provides methods to execute a command and undo the latest command. This structure allows the user to interact with the text editor seamlessly. When we use the command manager to execute commands, we can observe how text is added and undone, demonstrating the power of the command pattern in managing complex actions efficiently. Next, we will implement the chain of responsibility pattern, which helps in handling support requests by allowing different levels of support staff to manage issues based on their expertise. We start with an abstract class called support handler, which lays the groundwork for defining a chain of handlers. This class has a next handler property to hold the next handler in the chain and a set next method, which connects handlers together, allowing for a dynamic handling process. Now let's create specific handler classes for different levels of support. The junior support class checks if it can address a basic issue. If not, it passes the request to the next handler. Similarly, the senior support class handles advanced issues and forwards any other requests up the chain. Finally, the manager support class is positioned to handle all other issues, ensuring that every request is addressed irrespective of complexity. In the usage example, we instantiate the various support classes and set the chain's order. When we send different issue types, each handler responds appropriately based on its capabilities, demonstrating how the chain of responsibility pattern facilitates flexible issue management while decoupling senders from receivers in our support system. Now let's implement the Memento pattern, which enables an object to capture and restore its internal state without exposing its structure. We start by defining a Memento class that stores the internal state, represented here as a string. This class has a private constructor that initializes the state and a public method to retrieve it. Next, we create the editor class, which simulates a text editor. This class contains a private property for the content and methods to set and get its content. The critical feature of the editor class is the save method, which creates and returns a new Memento instance containing the current content of the editor. This allows the editor to save its state at any moment. Additionally, we implement the restore method, taking a Memento object to revert the content back to a previously saved state. This aspect of the pattern is especially useful for features like undo operations, where users want to switch back to their last saved content. Finally, in the usage section, we can see how to leverage this functionality by creating an editor instance, saving its state, and restoring it after modifying the content. This demonstrates the elegance of the Memento pattern in managing the internal state of objects efficiently. To summarize, behavioral design patterns offer a powerful toolkit for managing communication and responsibilities in software applications. Patterns like observer, strategy, command, chain of responsibility, and Memento each serve distinct purposes, promoting flexibility, clarity, and maintainability in your code. By applying these patterns, developers can create systems that not only meet current requirements, but are also adaptable to future changes. In today's lesson, we highlighted several behavioral design patterns and demonstrated how they can enhance the organization of your code. Stay tuned for our next lesson, where we will explore even more design patterns and their applications in TypeScript development. Thank you for joining. The strategy pattern is a powerful behavioral design pattern that encapsulates a family of algorithms within a common interface, making them interchangeable at runtime. In today's lesson, we will dive deep into this pattern, exploring its significance, advantages, and practical applications, particularly using TypeScript. So far, we learned about the significance of behavioral design patterns in managing object communication and responsibilities in software development. We covered patterns such as observer, strategy, command, chain of responsibility, and Memento, emphasizing their roles in promoting flexibility, maintainability, and clarity in code. In this lesson, we will cover the strategy pattern in detail and see how it can make our applications more adaptable. Now let's take a look at how we can define the common interface for our payment methods. We begin by creating the payment strategy interface, which serves as a blueprint for all payment methods. This interface specifies a single method, pay, which accepts an amount as a parameter. Every payment strategy will implement this method, ensuring that all payment types follow the same contract. Next, we will implement several concrete payment strategies that adhere to this interface. We create 3 classes: credit card payment, PayPal payment, and bank transfer payment. Each of these classes offers a unique implementation of the pay method. For instance, the credit card payment class logs a message indicating that a payment is made using a credit card, while the PayPal payment and bank transfer payment classes log their respective payment methods. This structure allows us to encapsulate the different payment behaviors and makes it easy to switch between payment methods at runtime, demonstrating the flexibility the strategy pattern provides. In summary, these classes not only fulfill the contract laid out by the interface, but also illustrate how easily we can introduce new strategies without affecting existing code. This encapsulation of payment logic supports clean and maintainable code. Next, we will implement the payment context class, which serves as the context for our payment strategies. This class will hold a reference to the payment strategy interface and be responsible for setting and executing the desired payment strategy. Within the class, we define a private variable strategy that will hold the current payment strategy. The setStrategy method allows us to assign a specific strategy dynamically, enabling the flexibility of switching payment methods at runtime without requiring alterations to the business logic. Now let's see how we can utilize the payment context in practice. After instantiating the payment context class, we first set the payment strategy to credit card payment and execute a payment of $100. The system will seamlessly call the pay method in the credit card payment strategy, demonstrating that the payment has been processed through this method. Subsequently, we change the strategy to PayPal payment and execute another payment of $150. Remarkably, the entire process remains unchanged in terms of the client code, showcasing the strategy pattern's core advantage, flexibility in behavior without modifying the existing code structure. Now let's implement the common interface for sorting algorithms. This sort strategy interface defines a single method, sort, which accepts an array of numbers and returns a sorted array. By establishing this contract, we ensure that any sorting algorithm we create will adhere to this structure, allowing for interchangeable usage within our sorting context. Next, we will define two specific sorting strategies, quicksort and mergesort. Each of these classes implements the sort strategy interface, providing its own version of the sort method. In the quicksort class, for instance, we log a message indicating the sorting method being used and return the sorted array using the native sort function. The same approach applies to the mergesort class. This encapsulation of the sorting algorithms allows us to add additional algorithms in the future without modifying existing code, adhering to the open-closed principle. Now let's take a look at how we integrate these strategies into a context. The sorting context class maintains a reference to a sort strategy and provides methods to set the desired strategy and sort the data. This setup not only promotes separation of concerns, but also enables dynamic algorithm selection at runtime, which enhances the flexibility of our sorting mechanism. Now let's take a look at how we can implement the strategy pattern through a practical example involving sorting algorithms. First, we create an instance of the sorting context class, which serves as the context that will allow us to utilize various sorting strategies. Then, we define an array of numbers that we want to sort. Next, we demonstrate the flexibility of the strategy pattern by setting the sorting strategy to quicksort. This is done through the setStrategy method, which updates the context to use this specific algorithm. By calling the sortData method with our data, we sort the array and log the result. Afterward, we switch the strategy to mergesort in a similar manner. Again, we use the setStrategy method to change the algorithm, and then call sortData to sort the same array using mergesort. This example illustrates how easily we can switch between different sorting algorithms at runtime. By utilizing the strategy pattern, we keep our client code clean, organized, and free from conditional logic, promoting a robust design and separation of concerns in our application. Now, let's implement the movement strategies for our characters using the strategy pattern. We begin by defining an interface, movement strategy, which will serve as a contract for different movement behaviors. This interface ensures that any class implementing it will provide a specific implementation for the move method. Next, we create several classes that implement the movement strategy interface, walk, run, and fly. Each class has its own version of the move method, where we can define the specific behavior for walking, running, or flying. For example, in the walk class, we have defined a method that logs walking to the console, representing the action when a character walks. Now let's create the character class, which will utilize these movement strategies. This class contains a private property to hold a reference to the current movement strategy. By implementing a method, setMovementStrategy, we allow the character to switch its movement behavior dynamically at runtime. The moveCharacter method invokes the move method of the assigned strategy, enabling the character to execute the corresponding movement action. This structure exemplifies how the strategy pattern allows for flexible and modular character behavior in a gaming context. Now let's see how we can implement movement strategies for our character using the strategy pattern. We start by creating an instance of the character class. Once our character object is instantiated, we can leverage different movement behaviors by setting various strategies. By invoking the setMovementStrategy method, we assign specific movement strategies, such as walking, running, and flying, to the character dynamically. After we set the movement strategy to walk, we call moveCharacter, which executes the specific movement behavior associated with the walk strategy, resulting in the output walking. Next, we switch the movement strategy to run using the same setMovementStrategy method and call moveCharacter again, producing the output running. Finally, when we change the strategy to fly and execute the movement method once more, it outputs flying. This flexibility exemplifies the power of the strategy pattern, allowing for seamless transitions between various behaviors without altering the character class's implementation. It emphasizes how the design pattern fosters adaptability, especially in gaming scenarios, where characters might change their movement modes based on different conditions or requirements. As we progress in our exploration of the strategy pattern, it's vital to understand how it aligns with the solid principles, particularly the open-closed principle, which states that classes should be open for extension, but closed for modification. With the strategy pattern, you can introduce new strategies without changing the existing code. This keeps your codebase sustainable and easy to evolve. To wrap up our discussion, let's summarize the highlights of what we covered today regarding the strategy pattern application. We explored how to encapsulate algorithms in a common interface, enabling interchangeable strategies at runtime. Through practical examples like payment processing, sorting algorithms, and character movements, we demonstrated how this design pattern enhances code maintainability, clarity, and flexibility. So remember, if you're looking to implement a solution in your organization where different behaviors are required, consider leveraging the strategy pattern. The power of encapsulation and the ability to swap algorithms at runtime are invaluable in modern software development. As we conclude this lesson, I hope you are excited to implement the strategy pattern in your projects. In our next lesson, we will continue exploring additional design patterns and their practical applications in TypeScript. Thank you for joining and have. The observer pattern is an essential behavioral design pattern that implements a system for objects to post events and other objects to subscribe to those events and act accordingly. This pattern is pivotal in systems where a change in one object necessitates a change in others, facilitating a loose coupling between components in your applications. So far, we learned about the strategy pattern, which allows for the selection of algorithms at runtime through a common interface. It has applications in scenarios like payment processing, sorting algorithms, and character movement in games, emphasizing benefits like maintaining clean and flexible code. In this lesson, we will delve into the observer pattern, exploring its implementation, advantages, and real-world applications, particularly using TypeScript. The observer pattern revolves around the concept of a subject, or observable, and observers. The subject maintains a list of observers and notifies them of any state changes. This design pattern is incredibly beneficial in scenarios like event handling systems, notification services, or any scenario where one object needs to inform others about changes without being tightly coupled to them. Let's illustrate this with a practical example of a weather station. The weather station can be the subject, which gathers data on temperature, humidity, and pressure. Various display units can act as observers and will update their display whenever there's a change in weather data. Now let's implement the observer interface, which will dictate how observers interact with the subject. We define an observer interface with an update method that takes in 3 parameters: temperature, humidity, and pressure. By establishing this method, we ensure that any class adopting this interface will implement a standardized way to handle updates whenever there's a change in the subject's state. Next, we will create the weatherData class, which serves as our subject that monitors a list of observers. This class contains an array of observers and initializes variables to store temperature, humidity, and pressure. The core functionality of this class includes methods to register and remove observers, ensuring that they can subscribe or unsubscribe from notifications seamlessly. The Notify Observers method is crucial, as it loops through each registered observer and invokes their update method, passing the current weather data. Finally, we provide a setMeasurements method that simulates new weather data. When this method is called, it updates the weather parameters and invokes Notify Observers to alert all registered observers of the change. This implementation encapsulates the observer pattern, facilitating effective communication between the subject and its observers. Now let's take a look at the implementation of our observer classes that react to updates in weather data. First, we have the Current Conditions Display class, which implements the observer interface. This class contains two private properties, temperature and humidity, both initialized to 0. The key method here is update, which is invoked whenever the weather data changes. When called, it updates the internal state with new temperature and humidity values, and then triggers the display method to show the current conditions in the console. Next, we will write the statistics display class, which also adheres to the observer interface and is designed to track temperature readings over time. It contains a private array called temperatures where it stores incoming temperature values. Using the update method, it adds the new temperature to this array. After storing the value, it calls the display method, which calculates the average temperature from all stored readings and logs it to the console in a formatted manner. Both classes exemplify how the observer pattern allows them to respond to changes in weather data independently while adhering to a common interface structure. Now let's implement the following code to see our weather data class in action along with the observer displays. We begin by creating an instance of weather data, which will serve as our subject, responsible for managing the observers and notifying them about weather updates. Subsequently, we instantiate two observers, current conditions display and statistics display. These display units will be registered with the weather data instance to observe changes in weather conditions. Next, we call the registerObserver method on the weather data object for each of our display instances, ensuring they are prepared to receive updates. This establishes the link between the subject and the observers. Whenever the weather data changes, both displays will respond accordingly. Now let's simulate some weather updates using the setMeasurements method on the weather data object. By passing in different temperature, humidity, and pressure values, we trigger notifications to all registered observers. As a result, the current conditions display will update and display the latest temperature and humidity, while the statistics display will compute and present the average temperature based on the updates it receives, demonstrating the dynamic capabilities of the observer pattern effectively. The beauty of the observer pattern lies in its flexibility and decoupling. The weather data class does not need to know anything about the observer's internal workings. It simply pushes updates and allows observers to handle their own state independently. This becomes incredibly useful, especially in larger applications where various components need to respond to changes without being tightly bound to the data source. When implementing the observer pattern, you'll find that it allows for a more modular and maintainable codebase. However, one must be cautious about memory leaks. It's important to ensure observers are properly removed when they are no longer needed, as failure to do so could lead to unintended consequences. Besides the weather station example, we can see the observer pattern in various real-world applications. Think about how social media platforms send notifications. When someone likes your post, that action needs to be communicated to you in real time. The platform acts as the subject, handling multiple users who need updates about different events like likes, comments, or messages. Another area where the observer pattern shines is in GUI frameworks. Consider UI components that need to reflect changes in data models. When the underlying data changes, the UI elements can automatically update to represent the current state. This dynamic observer relationship minimizes repetitive boilerplate code for updating UI elements and makes applications feel more responsive. The observer pattern also aligns well with the principles of reactive programming, where asynchronous data streams dictate the flow of data and updates within applications. Instead of employing common callbacks or event listeners in a convoluted manner, observers can handle notifications more seamlessly. On a performance note, consider a scenario where there are many observers registered. When a state change occurs, it's essential to think about the implications of notifying multiple observers. If the updates involve extensive computations or network requests, it could lead to slowdowns. In such cases, optimizations such as throttling or batch updates can be considered to keep performance in check. To solve for the potential performance pitfalls of the observer pattern, one could implement patterns like debounce effects, where updates are only sent after a certain grace period, reducing the frequency of notifications for rapid changes. Another practice is to have different levels of notifications. For instance, in a logging system, you may have varying levels of observers. Some may only want critical updates, while others might be interested in debug-level information. By structuring notifications like this, you can avoid bombarding all observers with redundant data. In conclusion, the observer pattern is an invaluable tool in a developer's toolkit, especially in creating responsive and flexible applications. By facilitating communication between subjects and observers without tight coupling, it enhances code maintainability and adheres closely to the principles of object-oriented design. So as we wrap up this lesson, remember that the observer pattern is not just a theoretical concept. It can play a significant role in your application designs, making your systems cleaner, modular, and easier to work with. In our next lesson, we will explore more design patterns and their practical applications, further enhancing our TypeScript skills and understanding of software architecture. Thank you for joining, and happy. In this lesson, we're diving into an exciting topic, behavioral patterns. These are crucial in software design as they help manage the state and behavior of objects over time. Think of it as crafting a lead character in a story. Over time, that character undergoes various transformations, influenced by their experiences, much like how our objects will behave depending on their internal states. So far, we explored the observer pattern, a design paradigm allowing objects to notify multiple observers about state changes without being tightly coupled. Remember our weather station example. It showcased how observers could display current conditions and statistical averages, enhancing the responsiveness of applications. Now, we will explore design patterns that help in managing the complexity of object behaviors as they progress through different states. Now let's see how we can implement the state pattern with a practical example in TypeScript. The core of this implementation is the state interface, which defines a handle method that each concrete state will provide its own implementation for. The context class plays a pivotal role as it maintains a reference to the current state instance, enabling it to delegate state-specific behavior through the request method. When we instantiate the context with an initial state, it allows us to invoke the request method, triggering the behavior of the current state. Here, we also have concrete state A and concrete state B, which implement the state interface and provide specific behaviors when their respective handle methods are invoked. This illustrates how the object's behavior can change dynamically without needing extensive conditional logic scattered throughout the code. Next, by calling the changeState method, we can seamlessly transition to a different state, showcasing the flexibility that the state pattern provides. This structure promotes clean, maintainable code by adhering to the single responsibility principle, allowing each state to encapsulate its specific responsibilities effectively. Now let's see how we can implement the Memento pattern using a text editor example to illustrate state management. Here, we define an interface called TextEditorState, which encapsulates the state of our text editor by storing the content and the cursor position. The EditorMemento class is responsible for holding this state in memory, allowing us to retrieve it when needed. In the main TextEditor class, we initialize the state and maintain a private array of EditorMemento instances, which serves as our history of states. Whenever the user types text into the editor, we update the state and immediately save this new state into the Memento array, ensuring that we can backtrack if necessary. The undo method plays a crucial role. It checks if there are any saved mementos, and if so, retrieves the most recent state to revert to it. This approach follows the principles of encapsulation, as it allows us to manage state changes without exposing the inner workings of the text editor. By integrating this pattern, we create a robust feature for undoing actions, enhancing the overall user experience in the application. Now let's take a look at the implementation of the iterator pattern. We begin by defining an iterator interface that specifies two essential methods, hasNext and next, which help us traverse through a collection of items without exposing its internal structure. The array iterator class implements this interface and provides the mechanics for iterating over an array. It keeps track of the current index and allows clients to check if there are more items available with the hasNext method and to retrieve the next item using next. Next, we create a collection class which serves as a container for our items. This class has a private array that holds these items and a method to add new items. Its getIterator method returns a new instance of the array iterator, enabling the client to begin traversing the collection seamlessly. Finally, in the client code, we see an example usage of the collection class. We create a collection of numbers, add 3 items, and utilize the iterator to traverse through them, printing each item to the console. This encapsulation of iteration logic allows for cleaner, more maintainable code and promotes the use of diverse collection types with a uniform interface. Now let's implement the template method pattern, which provides a framework for creating an operations blueprint while allowing subclasses to customize specific steps. In our example, we begin by defining an abstract class called meal, which serves as the template for the cooking process. The cook method, acting as our template method, outlines the steps involved in preparing a meal, preparing ingredients, cooking the meal, and serving it. Next, we use abstract methods for preparing ingredients and cook meal. Subclasses like pasta meal will provide their specific implementations for these methods, allowing for flexibility in how different types of meals are prepared. In the pasta meal class, we implement these abstract methods with details for preparing pasta and sauce and cooking the pasta. This structure allows us to add new meal types with their specific preparation steps without altering the overall cooking process defined in the meal class. Finally, when we create an instance of pasta meal and call the cook method, we observe the sequence of operations, demonstrating how the template method pattern effectively pots the behavior of the class while maintaining a consistent framework. This approach promotes code reuse and adheres to the principles of object-oriented design. With these behavioral patterns, state, memento, iterator, and template method, you're equipped to manage object behaviors intricately and elegantly. Each pattern has its own context of use, advantages, and potential drawbacks, so always assess which one fits your scenario best. In the next lesson, we'll shift gears to explore principles of functional programming, focusing on immutability, first-class functions, and higher-order functions that create more predictable and maintainable code. Thanks for watching, and see you in the next. The Memento pattern is a powerful design solution for managing an object state throughout an application without compromising encapsulation. This means you can capture and restore object states without revealing the inner workings or details of those objects. So far, we learned about behavioral patterns in software design, focusing on how they manage the state and behavior of objects. We examined the observer pattern through a weather station example and explored the state, memento, iterator, and template method patterns with practical TypeScript implementations. Each pattern allows for better organization and encapsulation of behaviors, making code more maintainable and flexible. In this lesson, we will cover the Memento pattern in depth and see how it can be implemented in TypeScript, showcasing its effectiveness in applications such as text editors or game states. The Memento pattern consists of three main components: the originator, the memento, and the caretaker. The originator is the object we want to capture the state of. The memento is an object that holds the internal state of the originator. Finally, the caretaker is responsible for managing the saved state. It stores and retrieves the memento from the originator when needed. This separation ensures that the originator's internal state remains hidden from the caretaker, adhering to the principle of encapsulation. Now let's see how we can implement the TextEditor class, which acts as our originator in the Memento pattern. This class maintains the internal state of the text editor, represented by a TextEditor state object that includes the content of the editor and the cursor's position. The type method allows users to add text to the content, updating the state each time new text is entered. After modifying the content, the method saves the current state into a stack of editor memento instances, ensuring that we can revert to this state later if needed. The undo method is crucial for restoring previous states. It retrieves the most recent editor memento from the stack and updates the internal state of the text editor to reflect that last saved state. If there are no mementos to undo, the current state remains unchanged. Finally, the getContent method provides access to the current text content, enabling users to view their ongoing work. This straightforward design effectively encapsulates the editing logic while leveraging the Memento pattern to allow for essential undo functionality, leading to a more manageable and user-friendly text editing experience. Now let's see how we can implement the TextEditor class, which acts as our originator in the Memento pattern. This class maintains the current state of the text editor, including the content being edited and the cursor position. The internal state is represented by an object that includes these properties, starting with an empty string for the content and a cursor position set to 0. As the user types text, the type method is called, which appends the input text to the existing content and subsequently saves this state by creating a new editor memento instance, pushing it onto the mementos stack. This ensures that each action can be reverted back to its previous state if needed. The undo method plays a crucial role in restoring the last saved state. It checks if there are any saved mementos, and if so, retrieves the last one, updating the current state accordingly. If no memento exists, the method simply retains the current state, ensuring the text editor remains functional even without previous states. Lastly, the getContent method allows users to retrieve the current text content, showcasing the effect of all editing and undo operations. Next, let's see how we can implement our text editor in action by demonstrating its core functionalities. We start by creating a new instance of the TextEditor class. This instance will allow us to interact with the text editing features. First, we type hello to begin our text input, followed immediately by world. At this point, the console log statement outputs the concatenated string hello world, showcasing the current content of our text editor. Now, after our text input is complete, we want to utilize the undo functionality to illustrate the Memento pattern in play. When we call the undo method, the last saved state, which includes the addition of world, is removed from the stack of mementos. This effectively reverts the content to hello by restoring the previous state. The subsequent console log confirms the action, displaying just hello. This process highlights how the memento pattern enables us to manage text changes seamlessly, allowing a user-friendly experience while editing. Now that we've seen the implementation in action, let's delve into why the Memento pattern is such a valuable addition to a developer's toolkit. One of its primary benefits is that it promotes clean separation of concerns while managing state changes. In our example, the text editor class handles the logic of editing, while the editor Memento class solely manages the internal state. This separation prevents tight coupling, which is crucial for maintainable code. Additionally, the Memento pattern enables features like undo and redo functionalities seamlessly. In scenarios where you want to track multiple states, you can enhance the stack to keep multiple Memento instances, allowing users to undo several actions rather than just the last one. The flexibility offered by this pattern can be particularly beneficial in complex applications, such as graphics editors, document editing software, or even games where object states change frequently. Now let's implement the text editor with limit class, which enhances our previous text editor by adding a cap on the number of Memento states stored. This design helps in managing memory more effectively, ensuring that the application doesn't retain an excessive number of states that could degrade performance over time. The class starts with the necessary attributes, including the current state of the text editor, an array to hold the mementos, and a limit to specify the maximum number of states that can be stored. In the constructor, we set this limit, which will be utilized whenever a new state is saved. Now let's look at the save method. It first checks if the array of mementos has reached the specified limit. If it has, the oldest memento is removed using the shift method, which ensures we only keep the most recent states. A new memento is then added to the stack, encapsulating the current state of the editor. The undo method functions similarly to the previous implementation, allowing users to revert to the last saved state while maintaining the overall functionality of the editor. This implementation showcases the benefits of the Memento pattern while keeping memory usage in check. In summary, the Memento pattern serves not just to capture the state of an object, but also to do so with a strong emphasis on encapsulation, ensuring that the internal details remain hidden from the outside world. We've walked through the implementation in TypeScript, examined how a simple text editor can utilize this pattern to allow users to type text and undo their actions effectively. We even explored how to limit the number of states saved, which adds a layer of elegance to managing memory. As we wrap up this lesson, keep in mind the significance of maintaining encapsulation while managing state effectively. The Memento pattern is just one of the many tools in your design patterns toolbox that can simplify your applications while enhancing usability. In our next lesson, we'll transition to functional programming principles, emphasizing immutability and higher-order functions that create more predictable and maintainable code. Thank you for tuning in, and see you next time as we continue to expand our program. The visitor pattern is a powerful design pattern that enables us to separate an algorithm from the objects on which it operates. This allows us to add new operations to existing object structures without modifying them. A very common use case for the visitor pattern is in static code analysis tools, where diverse elements of source code need to be analyzed, such as classes, methods, and variables, without changing their underlying structure. So far, we have learned about the Memento pattern, which provides a way to capture and restore an object's state while maintaining encapsulation. We discussed its key components and implemented a simple text editor class in TypeScript to illustrate its functionality. Now, we will shift our focus to the visitor pattern, exploring its use cases and implementations, particularly in the realm of static code analysis tools and similar scenarios. Now let's implement the shape interface in two specific shape classes, circle and rectangle. The shape interface requires an accept method, which takes a shape visitor as an argument. This method is crucial for enabling the visitor pattern, as it allows the shapes to be operated on by various visitors without altering their structure. Next, we define the circle class, which implements the shape interface by providing an accept method that invokes the visitCircle method on the visitor, passing itself as a parameter. This way, the visitor can perform operations specific to a circle. Similarly, we create the rectangle class. It also implements the shape interface and has an accept method that calls visitRectangle, allowing the visitor to handle rectangle-specific operations. By organizing our code this way, we maintain the independence of the shape classes from the operations performed on them, thus adhering to the principles of the visitor pattern. This sets the stage for extending functionality by simply adding new visitor implementations later, enhancing flexibility and maintainability in our codebase. Next, we will write the shape visitor interface and its implementation, the area calculator, which are crucial for calculating the area of different shapes using the visitor pattern. The shape visitor interface declares specific methods for each shape type, in this case, visit circle for circles and visit rectangle for rectangles. This setup delineates the operations that can be performed on the shape objects without changing their underlying structure. Now let's see how the area calculator class implements this interface. In its methods, the calculator provides functionality to compute the area of a circle based on the formula \pi r2 \, where radius is the property of the circle object, and for rectangles it multiplies the width by the height to determine the area. This modular approach allows us to separate the area calculation logic from the shape classes themselves, promoting easy extensibility. Additionally, the design permits adding new visitors for different operations, like calculating perimeter, without modifying the existing shape classes, exemplifying the main benefit of the visitor pattern, enhancing functionality while preserving existing code's integrity. Now let's see how we can implement the visitor pattern by creating an array of shapes and utilizing our area calculator. We start by defining an array named shapes that holds instances of circle and rectangle. Each shape is instantiated with appropriate parameters. The circle is created with a radius of 5, and the rectangle is initialized with a width of 10 and a height of 20. Next, we instantiate the area calculator, which is a visitor designed to compute areas of the shapes. We then iterate over each shape in the shapes array using the forEach method. For each shape, we call the accept method and pass the area calculator as an argument. This is where the visitor pattern shines. Each shape delegates the area calculation to the visitor without needing to know the specifics of how this is done. The result is a calculated area for each shape, which we then log to the console. This structure exemplifies the flexibility of the visitor pattern, as it allows for easy addition of new shape types or operations without altering the existing codebase. Such extensibility is vital in larger applications, where operations may continually evolve. Now let's take a look at how we can define the structure of our abstract syntax tree, ASD, using the visitor pattern. We begin by creating an ASD-node interface, which requires each node to implement an accept method that takes a code analyzer visitor. This design allows various node types to accept different visitors without modifying their internal structure. Next, we implement specific node classes: class node, method node, and variable node. The class node class encapsulates information about a class name and an array of methods, while method node stores the name of a method. The variable node keeps track of the variable name alongside a Boolean indicating its usage status. Importantly, each of these classes implements the accept method to call the appropriate method of the visitor, delegating analysis tasks. This setup supports extensibility. As new node types emerge in the ASD, they can seamlessly integrate into our analysis framework without altering existing code. By structuring the nodes in this manner, we create a solid foundation for conducting static code analysis, ensuring that our tool can efficiently traverse and analyze various components of the codebase while maintaining object independence and integrity. Next, let's implement a simple code analyzer using the visitor pattern, which specifically targets the detection of unused variables in code. We start by defining the code analyzer interface, which outlines the methods our analyzer will need to handle various node types like classes, methods, and variables. This helps to ensure a structured approach where our analyzer can traverse the abstract syntax tree, ASD, seamlessly. Now let's take a look at the implementation of the unused variable analyzer class. This class implements the code analyzer interface and contains a private array to keep track of any unused variables it encounters during analysis. The visit class method is responsible for iterating over all methods in a class and applying the visitor pattern on each one, effectively allowing the analyzer to drill down into the method logic. When analyzing a method with the visit method, we log the method's name. In a full implementation, we would check for variable usage here. For each variable, the visit variable method checks if it's marked as unused, adding it to the unused variables list if necessary. Finally, we have the report unused variables method, which provides a summary of any unused variables found, reinforcing the analyzer's functionality in enhancing code quality through unused variable detection. Now let's implement the following code to create an abstract syntax tree, ASD, that will be analyzed for unused variables. We start by defining a new class node named myClass, which contains an array of nodes representing methods and variables. In our example, we incorporate a method called myMethod alongside two variables, unused var1, marked as unused, and used var, which is utilized within the method. This setup allows us to mimic a section of code in an application, encapsulating both functional and non-functional elements. Next, we instantiate the unused variable analyzer, which is our custom code analyzer designed to traverse the ASD. By calling the accept method on our class node, we allow the analyzer to visit each part of the ASD. It navigates through the methods and variables, invoking appropriate analysis methods. Finally, we invoke report unused variables to output any unused variables identified during the analysis. This exercise demonstrates the visitor pattern's utility in traversing and assessing complex structures, showcasing its strengths in maintaining clean code while facilitating detailed static analysis. In conclusion, the visitor pattern is a valuable design pattern that allows for operations on object structures without requiring the classes of the elements to change. We explored various use cases, particularly focusing on static code analysis tools, where this pattern facilitates the analysis of different components of a codebase while ensuring maintainability and extensibility. The ability to easily add new operations and traverse through objects without altering their designs makes the visitor pattern a powerful tool in software design. As we conclude this session, be sure to reflect on how the visitor pattern can be applied, not just in static analysis, but in any scenario where operations must be performed across varied objects while maintaining their independence. In our next lesson, we will delve into functional programming principles, where we will emphasize immutability and higher-order functions that create more predictable and maintainable code, continuing our journey into mastering software design. Thank you for joining, and I can't wait to see you in the next. Functional programming is a paradigm that uses functions as the primary building blocks to construct larger programs. It's a transformative approach that enhances code clarity, reusability, and maintainability. In this lesson, we'll explore the key concepts that define functional programming while using TypeScript as our primary tool for demonstration. So far, we learned about the visitor pattern, which allows operations to be performed on object structures without changing the classes they belong to. We implemented this pattern using shapes and an area calculator to illustrate its flexibility and ease of adding new operations. Additionally, we explored its application in static code analysis tools, demonstrating how it can analyze different components of code while maintaining a clean structure. Now we will shift our focus to functional programming principles, emphasizing immutability and higher-order functions. Now let's dive into a declarative approach to summing even numbers using TypeScript. First, we create an array of numbers from 1 to 10 using the arrayFrom method, which provides a clean way to generate an array with a specific length and populate it with values. In this case, we use a mapping function that fills the array with numbers from 1 to 10 based on their index. Next, we utilize the filter method to extract only the even numbers from our array. This function takes a predicate and retains elements that return true, effectively allowing us to define our criteria for filtering. Following the filtering step, we apply the reduce function to sum the filtered even numbers. The reduce method takes a callback function that accumulates the total, starting from an initial value of 0. Finally, we log the result to the console, which will output 30, demonstrating how this concise and readable code aligns well with the principles of functional programming by emphasizing clear intent and immutability. Now let's explore the concept of pure functions in functional programming through a simple example. The add function takes two numbers as parameters and returns their sum. This function is considered pure because it always provides the same output, 5, when invoked with the inputs 2 and 3, regardless of when or how many times it's called. There are no side effects involved. It does not change any external state or rely on external variables. Next, we will consider its counterpart, an impure function named incrementandlog. This function takes a value and increments a global count variable each time it is invoked, thus modifying external state. Moreover, it logs the updated count to the console, introducing a side effect. Unlike the add function, the output of incrementandlog is not solely determined by its input, making it less predictable and harder to test. This contrast highlights the importance of pure functions in ensuring code reliability and ease of understanding, which are core principles in functional programming. Now let's take a look at a practical application of higher-order functions through a code example. In this implementation, we define a function named executeOperation that takes two numbers and another function as parameters. This higher-order function utilizes the past function, referred to as operation, to perform a calculation on the two numbers. Next, we create two simple functions, add and multiply, that each define a specific mathematical operation, addition and multiplication, respectively. By passing these function references to execute operation, we can easily switch between different operations without altering the structure of our code. This demonstrates the flexibility and composability of higher-order functions. By calling execute operation with the add function, we get the sum of 5 and 3, resulting in 8. Similarly, invoking execute operation with the multiply function allows for multiplication of the same numbers, yielding 15. This illustrates how higher-order functions can enhance code reusability, making it straightforward to apply different operations just by supplying different function arguments. Now let's see how we can implement immutability in our TypeScript code. By using the const keyword, we declare a variable named numbers, which holds an array of integers from 1 to 5. It's crucial to notice that since this variable is declared with const, its reference cannot be changed, enforcing immutability and protecting it from accidental modifications. Next, we utilize the map function to create a new array called doubled. This function takes a callback that doubles each number in the numbers array. Importantly, the original numbers array remains unchanged, which is a key aspect of immutability in functional programming. After using map, we log both the numbers array and the doubled array to the console. The output clearly shows that while we've created a new array with doubled values, the original data structure is preserved, effectively showcasing how immutability helps maintain the integrity of our data and prevent side effects in our applications. Such practices not only enhance code safety, but also improve readability and maintainability, aligning with the principles of functional programming. Now let's take a look at how recursion operates in programming, particularly through the example of calculating a factorial. The first function, factorial, illustrates a classic recursive approach where the function calls itself. When the input n is 1 or less, the function returns 1, which serves as the base case, effectively stopping the recursion. For any other value of n, the function computes n multiplied by the factorial of n1, steadily decreasing the problem size until it reaches the base case. This elegantly demonstrates how recursion can simplify the process of tackling complex problems by breaking them down into smaller, more manageable pieces. Next, we will implement a tail recursive version of this factorial calculation with the factorial tail function. In this version, we introduce an additional parameter, accumulator, which helps keep track of the result during recursive calls. The crucial change here is that the recursive call is the last operation in the function, allowing some languages to optimize this into a loop, avoiding stack overflow issues that often arise with deep recursion. Both functions ultimately produce the same result, but showcase different recursive strategies, enhancing our understanding of problem-solving paradigms in functional programming. Now let's see how we can implement function composition in our code. We begin by defining two simple functions, double and increment. The double function takes a number as input and returns its double, while the increment function increases the input by 1. This modular design allows us to independently define small, reusable functions that can perform specific tasks. Next, we create a new function called double and increment using an arrow function. This function takes a number as an argument and employs function composition by first passing that number to the double function and then feeding the result into the increment function. This showcases the power of combining smaller functions into one cohesive operation. Lastly, when we call double and increment 3, the input number 3 is doubled to become 6, and then incremented to yield a final output of 7. This example illustrates how function composition enables us to construct complex operations from simpler, well-defined functions, enhancing code clarity and maintainability in the functional programming paradigm. In summary, functional programming is not just about using functions, but about leveraging the full power of those functions to create clean, reusable, and maintainable code. We covered key concepts like declarative programming, pure functions, higher-order functions, immutability, recursion, and function composition. With these fundamental ideas, you can unlock a new level of programming elegance in your TypeScript applications. In this lesson, we're diving deep into the core functional structures that form the backbone of functional programming. These structures enhance how we work with data in a functional style, focusing on composability and maintainability. So far, we learned that functional programming is a paradigm focusing on the use of functions as primary building blocks for enhanced code clarity and maintainability. We covered key concepts such as declarative versus imperative programming, pure functions, higher-order functions, immutability, recursion, and function composition. As we continue, we will explore these concepts further by examining practical functional structures, namely functors, applicatives, semigroups, monoids, and traversables. Now let's implement a functor interface in TypeScript to demonstrate how we can work with functors. The functor interface defines a single method called map, which takes a function as an argument and applies it to the value contained within the functor. This allows us to transform the value without altering the structure of the functor itself. Next, we create a box class that implements the functor interface. The box class serves as a simple container for a value and provides a constructor to initialize that value. Within this class, we implement the map method, which creates a new box containing the result of applying the provided function to the internal value. To illustrate how this works, we instantiate a box with a value of 5 and call the map method with a function that doubles the value. As a result, we obtain a new box that holds the transformed value 10. This example effectively showcases the core idea of functors. They allow us to work with values in a way that maintains their original context while still enabling meaningful transformations. Now let's take a look at how we can implement an applicative interface and extend our box class to support the concept of applicatives. In this code, we define an applicative interface that extends the existing functor interface, introducing an apply method that allows for the application of a wrapped function to a wrapped value. The box class is then updated to implement this interface, providing the necessary functionality for applicative behavior. Within the box class, we maintain the initial structure while adding the apply method. This method takes another box instance containing a function and applies that function to the value stored in the current instance of box. This enables us to work with functions that are themselves wrapped in a context, allowing for a seamless application of transformations. Finally, the example usage demonstrates how to create a box with a numerical value and another box, wrapping a function that doubles this value. By invoking the apply method, we can effectively apply the wrapped function to the wrapped value, yielding a new box containing the result of this operation, further illustrating the power of applicatives in functional programming. Now let's implement a semigroup interface and a sum class to illustrate how semigroups can effectively combine values. The semigroup interface defines a single method, concat, which takes another instance of the same type as an argument and returns a new instance that represents the result of combining both instances. In our sum class, we implement the semigroup interface specifically for numbers. This class is designed to encapsulate a numeric value and provides the concat method to allow two sum instances to be combined by adding their internal values together. The result is a new sum object whose value is the total sum of the two original values. Additionally, to access the internal value of our sum instance, we define a getValue method. This enables us to easily retrieve the numeric value after performing the concatenation. For example, by creating two instances of sum, one with the value of 5 and the other with 10, we can use the concat method on the first instance, passing the second instance as an argument. The output of this operation will give us a new sum object, and calling getValue will yield the total of 15, demonstrating the utility and functionality of semigroups in combining values. Next, we will extend our sum class to illustrate the concept of monoids in functional programming, specifically by implementing the monoid interface. This interface builds upon the semigroup structure, adding a crucial empty method that returns the identity element for the operation, in this case, the identity element for summation, which is 0. In our modified sum class, we define the constructor for creating instances with a numeric value and implement the concat method to combine two sum objects by summing their values. The newly added empty method constructs a sum instance that represents the identity element, ensuring that any other sum instance can be combined with this identity without affecting its value. As we explore the usage of our sum class, we'll create instances such as sum1 and sum2 to represent specific numerical values. When we invoke the empty method on sum1 to obtain the identity element and then concatenate it with sum1, the output confirms the monoidal property. The result retains the original value of 5, demonstrating how identity elements operate within monoidal structures. Now let's take a look at how we can implement traversables in TypeScript. We begin by defining a traversable interface that extends the functor interface, introducing a traverse method. This method is crucial, as it applies a given function to each element of the traversable and expects that function to return an applicative. The results from the function application will then be combined. Next, we create a list class that implements this traversable interface. In the constructor, we accept an array of elements which will be stored privately. We also implement the map method, allowing us to transform the elements while ensuring the structure of the list remains intact. The core functionality, however, resides in the traverse method. This method maps the input function over the list's elements, resulting in an array of applicatives. To combine these applicatives into a single output, we employ the reduce method, sequentially applying the apply method to aggregate the results. In our example usage, we create a list instantiation and apply the traverse method with a function that doubles each value, demonstrating how traversables can elegantly handle collections while utilizing the power of applicatives. As we wrap up, we've explored practical functional structures that broaden our understanding of functional programming principles. Functors, applicatives, semigroups, monads, and traversables provide us with powerful tools to create clear, maintainable, and reusable code in TypeScript. By leveraging these structures, we can build complex and expressive code while adhering to the principles of functional programming. Remember, the key takeaway here is to embrace these structures as you write TypeScript code. They not only enhance your code's clarity, but also make it robust and adaptable. Each of these structures can be built upon and combined with other functional programming principles to create highly efficient and elegant solutions. So go on and incorporate these concepts into your next TypeScript projects. Monads are a powerful and often misunderstood concept in functional programming, providing a structure for chaining operations and handling side effects in a consistent manner. They serve as a bridge between pure functional programming and real-world scenarios, making them essential for clean coding practices. In this lesson, we will break down what monads are, how they work, and why they are so useful, ensuring you grasp their significance in TypeScript programming. So far, we covered functional programming concepts such as functors, which allow us to map functions over values, applicatives for applying wrapped functions, semigroups and monads that help us combine values, and traversables for applying functions contextually to data structures. Now we will dive into monads, understanding their structure, behavior, and application. To start, let's define what a monad is. In essence, a monad is a design pattern used to handle computations in a functional programming paradigm. More formally, a monad must satisfy three key properties. It has a type constructor that wraps values into monadic types. It provides a way to apply functions to these wrapped values while maintaining the monadic context, and it ensures that operations can be combined in a consistent manner through monadic laws, namely, the left identity, right identity, and associativity laws. At its core, a monad must implement two primary functions: bind, often represented as flatmap in TypeScript, and of, also known as unit. The of function wraps a value into a monadic context, while the bind function allows for the chaining of computations. Before diving into some TypeScript examples, let's explore these concepts further with a conceptual example. Imagine we are working with a box that contains a value. If we want to apply a function that transforms this value, we traditionally would take the value out of the box, apply the function, and then return a new box. This is fine, but when dealing with multiple transformations, it can quickly become inconvenient. This is where monads shine. They allow us to work seamlessly with the value inside the box without manually extracting it. Now let's implement the box class, which serves as our basic monad structure. This class encapsulates a value within a box, providing a clean way to handle and transform it without directly accessing the raw value. We start by defining a constructor that initializes the box with a given value. The static of method allows us to create a new box instance, effectively wrapping a value into our monadic context. Next, we introduce the map method, which applies a provided transformation function to the value inside the box and returns a new box containing the transformed value. This method is crucial as it maintains the context of the box while allowing safe manipulation of the encapsulated value. We also implement flatmap, which takes a function that returns another box. This allows chaining multiple operations seamlessly by applying subsequent transformations without extracting the value manually. To demonstrate the utility of our box class, we use it to multiply a value inside the box by 2, resulting in a new box. Additionally, we can chain operations using flatmap, enabling us to first increment the value by 2 and then multiply it by 3, showcasing the power of monads in composing functions while keeping the context intact. Next, we will explore the laws of monads by implementing examples that demonstrate the left and right identity laws. First, let's examine the left identity law. In our code, we define a constant value of 5 and a function, add2, which takes a number and returns a box containing that number increased by 2. We then wrap our value 5 in a box using the box of method and apply add2 using flatmap. The result stored in left identity is the value within the box, which we retrieve using getValue. In doing this, we confirm that wrapping the value in a monad and applying a function produces the same outcome as directly applying the function to the value, thus validating the left identity law. Next, we illustrate the right identity law. Here, we take a previously created box and apply flatmap with boxof. The expectation is straightforward. This operation should return the original value contained in the box. By accessing the value through getValue, we confirm that the right identity law holds true, demonstrating how these operations effectively work within the monadic context. Now let's see how we can implement the associativity law for monads using a practical example. In this code, we define two functions, multiply by 2 and subtract 3, each returning a wrapped value in a box. This allows us to transform the value contained within the box while adhering to the monadic structure. We first apply multiply by 2 to the boxed value using flat map, followed by subtract 3, resulting in result A. In this scenario, the transformations are executed sequentially on the value from the original box. This illustrates how we can maintain context while chaining operations. Next, we explore an alternative chaining approach with result B, where we wrap the first transformation in an anonymous function that uses flatmap again to apply subtract 3. This grouping shows that the sequence of operations does not affect the final output. Both result A and result B yield the same result of 7, confirming the associativity law. This example effectively highlights the strength of monads in allowing us to compose functions seamlessly while ensuring consistent outcomes. Now let's implement a promise-based monad called effect, which is designed to manage asynchronous operations effectively. The effect class encapsulates a function that returns a promise, allowing us to work with asynchronous data in a clean manner. It provides a static method that enables us to wrap a given value into an effect, ensuring it is handled as a promise. This is key in functional programming, where maintaining context is critical. Next, we'll see the flatmap method, which allows us to chain operations seamlessly. By taking a function that returns an effect, flatmap ensures that each resulting promise is awaited before it returns the final result. This chaining is essential for building complex asynchronous workflows without losing the context of previous values. To demonstrate usage, we define a simple asynchronous function, fetchData, that simulates fetching data using a promise. By using the effectOf method to create an initial effect and subsequently chaining it with flatmap, we are able to manage the flow of data from one asynchronous operation to another. Finally, calling run executes the operation, providing us with data after the completion of the asynchronous tasks, showcasing the power of monads in handling side effects. Now let's implement the maybe monad, which provides a clean way to manage values that might be absent. The maybe class encapsulates an optional value, allowing us to abstract away the complexity of checking for null or undefined directly in our logic. We start by constructing the class with a constructor that optionally accepts a value. The static method of creates an instance of maybe, ensuring that we correctly wrap values into our monadic structure. To check if the value is present, the isNothing method returns a boolean indicating whether the stored value is undefined or null. The power of the maybe monad shines with the flatmap function, which lets us chain operations while handling potential absence gracefully. If the value is missing, the method returns a new maybe instance without a value, thus preventing runtime errors associated with null checks. Finally, the getValue method allows us to retrieve the value safely, returning undefined if there's no value. Through this implementation, we can see how the maybe monad simplifies working with optional values, resulting in cleaner, more maintainable code as we compose operations seamlessly while managing absent states. As we wrap up this exploration of monads, it is essential to highlight their role in enhancing functional programming. Through consistent behavior governed by laws and powerful structures for chaining operations, monads provide a robust framework for writing clean, maintainable, and expressive code. They enable us to abstract away complexities such as side effects, asynchronous operations, and optional values, allowing developers to focus on the logic rather than error handling. Monads may initially seem complicated, but once understood, they become invaluable tools in your programming toolkit. As you apply monadic concepts in TypeScript, remember the principles we've covered, the laws governing their behavior, their use in managing side effects, and how they enable clean composition of functions. So as you head into your next projects, don't shy away from employing monads. They unlock powerful patterns and help you write better, more resilient code. When we delve into reactive programming, we're stepping into a paradigm that is all about handling dynamic data flows and the propagation of change. It emphasizes the way we build applications around data streams and the transformations applied to those streams. Today, we will explore the three key concepts of reactive programming: observables, operators, and subscribers, which are crucial for creating responsive and efficient software applications. Now let's see how we can implement an observable that emits a series of numbers. In this example, we start by importing the observable class from the RxJS library. We then create a new observable called numObservable, which takes a subscriber function as its parameter. Inside this function, we initialize a count variable at 0 and set up an interval timer using setInterval. With each tick of the interval, the observable emits the current count value using subscriber, next count plus plus. This means that every second the observable will emit the incremented count, starting from 0. When the count exceeds 5, we call subscriber complete to indicate that no more values will be emitted, and we also clear the interval to stop further emissions. Following the observable's definition, we subscribe to it by providing two handlers, one for the emitted values, next, and another for completion, complete. When a value is received, it logs the message to the console, and upon completion, it logs a message indicating that the observable has finished emitting. This approach showcases how observables can encapsulate complex timing logic while offering a clean and efficient way to manage asynchronous data streams. Now let's see how we can implement an observable that doubles the emitted values from our previous example. First, we import the map operator from the rxjs/operators package, which allows us to manipulate the emitted values. We create a new observable, doubled observable, by using the pipe method on num_observable, our original observable. The pipe method helps us compose multiple operators into a single observable stream. Inside the pipe, we apply the map operator, where we specify a function that takes each emitted value and returns its double. This means that whenever num_observable emits a value, the map operator transforms that value by multiplying it by 2 before passing it on. Next, we subscribe to doubled observable, providing an object with next and complete methods. The next method handles each transformed value, logging it to the console with the prefix doubled received. The complete method indicates when the observable has finished emitting values. Thus, when the original observable emits numbers from 0 to 5, the subscriber will receive and log the doubled results, ranging from 0 up to 10, demonstrating the ability to easily transform data streams using operators in reactive programming. Now let's take a look at how we can implement a multicast mechanism using a subject. A subject in RxJS is unique because it can act both as an observable and an observer, allowing multiple subscribers to react simultaneously to emitted values. In our code, we start by creating a subject that allows us to emit numbers, enabling multiple subscribers to listen for those emissions. Next, we define two subscribers, each logging the received value to the console with a distinct message. This illustrates the concept of multiple subscribers reacting to the same emitted data. When we call the next method on the subject, both subscribers receive the emitted values at the same time. Specifically, when we emit the numbers 1 and then 2, both subscriber 1 and subscriber 2 log these values concurrently. This demonstrates the powerful capability of subjects to share emitted values among multiple observers, providing flexibility in handling dynamic data flows efficiently. By utilizing subjects, you can create a more interactive and responsive application that reacts to changes in real time. Now let's see how we can implement an observable that fetches user data from an API. In this code snippet, we define a function, fetchUserData, which takes a user ID as an argument and returns a new observable. Inside this observable, we handle an HTTP fetch request to retrieve user data from the designated API endpoint. This approach encapsulates the asynchronous operation, allowing us to manage the flow of data seamlessly. As the fetch request is executed, we process the response by converting it to JSON before notifying subscribers with the fetched data. If the data fetch is successful, we call subscriber next data to emit the fetched user information and subsequently invoke subscriber complete to indicate that the observable has finished emitting values. However, in case of an error, we catch it and call subscriber error to notify subscribers of the failure. Next, we utilize the RxJS pipe method to apply operators such as map and catch error. The map operator is used to transform the emitted user information, extracting the user's name in a formatted string. Meanwhile, the catch error operator allows us to handle potential errors gracefully. Finally, we subscribe to the observable, logging the resulting message and handling any errors that arise during the data fetching process. This structured approach exemplifies the elegance and responsiveness of reactive programming. To sum up, a solid understanding of reactive programming revolves around three key concepts: observables, operators, and subscribers. By utilizing these components effectively, you can handle complex data flows with ease and create applications that are both responsive and scalable. In our journey, we've seen how observables can emit values over time, how operators like map allow us to transform this data, and how subscribers can react to these emitted values. So far, we learned about the basics of reactive programming, including observables, operators, and subscribers in TypeScript. Through practical coding examples, we explored how to navigate asynchronous operations and manage data flows effectively. In our next lesson, we will elaborate further on error handling in reactive programming, discuss different kinds of observables, and how to integrate reactive programming patterns in large applications. Prepare yourselves for even more exciting reactive challenges. Now let's see how we can implement a simple promise in TypeScript to simulate fetching user data. We define a function named fetchUserData that accepts a userid as an argument and returns a promise. Inside this function, we utilize the promise constructor to create a new promise. This promise uses setTimeout to mimic an asynchronous operation that resolves after 1 second. If the provided userid is 1, the promise resolves with an object representing the user, including an ID and a name. If the userid is anything other than 1, the promise rejects with an error message indicating that the user was not found. This structure allows us to handle the result of our asynchronous operation in a clear and more manageable way. Next, we will write a call to our fetchUserData function with a valid user ID, which will demonstrate how we can gracefully handle both the resolved and rejected cases using the then and catch methods. When the promise resolves successfully, we log the user's name. If it fails, we catch the error and log the corresponding message. This clear separation of success and error handling is one of the strengths of using promises in asynchronous programming. Now let's take a look at how we can implement a new function that simulates fetching posts associated with a user. We define the fetchUserPosts function, which takes a userid as an argument and returns a promise that resolves after a 1-second delay. Inside this function, we mimic an asynchronous API call using setTimeout to simulate a network request, similar to our earlier user data fetch. Next, we can see how to incorporate this new function into our existing promise chain. After successfully fetching the user data, we log the user's name to the console. Importantly, by returning the fetchUserPosts user D promise, we can seamlessly chain another, then block that will execute once the post-fetching operation completes. This allows us to maintain a clean and manageable structure, avoiding nested callbacks. Finally, by adding a catch block at the end, we ensure that if any error occurs during these asynchronous operations, it will be handled in a centralized manner, enhancing error management throughout the code. This approach demonstrates the elegance and readability that promises bring to handling multiple asynchronous actions in JavaScript and TypeScript. Now let's take a look at how we can implement PromiseAll, which allows us to execute multiple asynchronous tasks concurrently. In our example, we are fetching user data and the last 3 blog posts simultaneously using 2 functions, fetchUserData and fetchUserPosts. By passing an array of these 2 promises to PromiseAll, we enable concurrent execution of these asynchronous operations. The response from both promises will be available as an array once they resolve, which we can easily destructure into user and posts. This approach not only simplifies our code, but also optimizes performance, as both operations can run simultaneously rather than sequentially. If either of these promises rejects, it will trigger the catch block, allowing us to gracefully handle any errors that may occur during the fetching process. This means that if there's an issue with fetching either the user data or the posts, we will be notified through a meaningful error message. Thus, using PromiseAll is a powerful way to manage concurrent asynchronous tasks while ensuring robust error handling. Now let's implement a timeout feature using PromiseRace, which will allow us to manage the user data fetch along with a timeout promise. We begin by defining a function called timeoutPromise that takes a duration in milliseconds as an argument. Inside this function, we create a new promise that will automatically reject after the specified time using setTimeout. This simulates a scenario where the operation might exceed a desired time limit. Next, we utilize PromiseRace to initiate both our user data fetch and the timeout promise simultaneously. The PromiseRace method will return a promise that settles as soon as one of the promises in the iterable resolves or rejects. In our case, if the user data fetch completes successfully within 2 seconds, we will see the user's information logged to the console. However, if the fetch takes longer than our specified timeout, the timeout promise will reject first, effectively allowing us to capture this as an error. This is particularly useful for managing asynchronous operations where speed is critical, ensuring we can handle scenarios when an operation hangs or exceeds acceptable time limits. Now let's take a look at how we can implement error handling in our promise-based approach. After fetching user data, it's crucial to manage potential errors that could arise from the asynchronous operation. Here, we use a combination of the then, catch, and finally methods to handle both success and failure scenarios systematically. When we call the fetchUserData function with a user ID, the then method allows us to process and log the user's name if the operation is successful. However, if the user ID is invalid, the catch method will capture the error and log an appropriate message. This structured error handling ensures that any issues are managed gracefully without crashing the application. Additionally, the inclusion of the finally method is particularly noteworthy, as it executes a final block of code regardless of whether the promise was fulfilled or rejected. In this case, it logs fetch operation complete. This guarantees that the message is displayed regardless of the outcome, providing a clean way to perform common post-processing tasks, whether in case of success or error. This pattern exemplifies how promises enhance control over asynchronous flows, making the code easier to read and maintain. Now let's implement the following async function to display user information along with their posts. This function is defined using the async keyword, which allows us to use await within its body, making it easier to work with promises. The function begins with a try block where we use await to pause execution until the promise returned by fetch user data, user ID, resolves. Once the user data is successfully fetched, we log the user's name to the console. We then proceed to fetch the user's posts by calling fetch user posts user ID, again using await to ensure that we wait for the promise to resolve before moving forward. After the posts are retrieved, their titles are printed in a formatted manner within a loop. Error handling is an essential aspect of this function, achieved with the catch block. Any error encountered during the promise resolutions will trigger this block, allowing us to log a useful error message. Finally, irrespective of the outcome, we have a finally block that ensures a completion message is logged, signifying the end of the fetch operation. This combination of try, catch with finally not only enhances readability, but also provides a structured approach to managing asynchronous tasks. In summary, promises represent a significant advancement in handling asynchronous programming in JavaScript and TypeScript. They provide a robust, clear, and manageable way to work with asynchronous operations, transforming the reactive programming landscape. We've covered everything from the basics of promises, including how to create and use them, to chaining promises, handling multiple concurrent promises with PromiseAll, and using promise race for timeouts. Additionally, we highlighted the importance of error handling, including the use of finally, and explored async await for a more synchronous code style. As we wrap up our exploration of promises and futures, remember that mastering these concepts not only simplifies your coding tasks, but also enhances the efficiency and maintainability of your applications. Our next session will dive deeper into error handling strategies, different types of observables, and integrating these reactive programming principles into large applications. Stay tuned and keep. Now let's see how we can create a basic observable that emits a sequence of numbers. We start by importing the observable class from the RxJS library, which is essential for working with observables. Next, we define a new observable called numObservable. Within this observable's execution function, we utilize the next method to emit the numbers 1, 2, and 3 sequentially. By following these emissions with a call to complete, we signal that there will not be any further values emitted, effectively ending the stream. After creating our observable, we subscribe to it to react to the emitted values. The subscribe method takes an object that defines two handlers, one for processing each emitted value and another for handling completion. In this case, we log each received value to the console, as well as a message indicating that the observable has completed. This example effectively demonstrates the basic mechanics of observables, showcasing how we can initiate data streams, emit values, and subscribe to observe and react to those values in a straightforward manner. Now let's see how we can implement an observable that emits a sequence of values over time using the interval function from RxJS. In this code, we first import the necessary functions from the RxJS library, specifically interval and take. The interval function creates an observable that emits an increasing number every second, which we can control by specifying the interval duration in milliseconds. By piping this observable through the take5 operator, we are instructing it to only emit the first 5 values before completing, keeping it efficient and preventing unnecessary emissions. When we subscribe to this observable, we define an object containing next and complete methods. The next method logs a message to the console with the emitted value, displaying timer tick followed by the current count. This allows us to see each tick as it occurs every second. Once the observable completes after emitting 5 values, the complete method is invoked, logging timer completed. This example illustrates how observables can seamlessly handle time-based events, making it easy to manage asynchronous data that evolves over intervals. Next, we will write the following code to illustrate how to combine multiple observables using the combine_latest operator. In our example, we first import the required functions from the RxJS library, combine_latest and of. We then create 2 simple observables, first_name and last_name, which use the of function to emit static values, John and Doe, respectively. Now let's see how we can implement the combine_latest operator by passing an array containing both first name $, and last name $. This operator will listen for the latest emitted values from both observables and combine them into a single observable called full name $. When we subscribe to full name $, we specify a listener that takes the emitted values as an array. This allows us to access the combined first and last names easily. Finally, within the subscription, we log the constructed full name to the console. This approach exemplifies how reactive programming with observables can dynamically update derived values in response to changes in the source observables, making it especially powerful for creating interactive and responsive applications. Now let's see how we can implement a solution that captures click events using observables. In this code snippet, we start by importing the necessary functions from the RxJS library, specifically from event and map. The fromEvent function enables us to create an observable that listens for specific events on a DOM element. In this case, a button we assume has the ID myButton. Next, we set up our observable, clicks $, which emits a value each time the button is clicked. By using the pipe method alongside the map operator, we transform the emitted mouse event into a more useful format that includes the X and Y coordinates of the mouse pointer at the time of the click. This mapping enhances the data emitted by our observable, allowing us to work with the X and Y values directly. Finally, we subscribe to the clicks $, observable. Each time the event is emitted, we log the click coordinates to the console, demonstrating how easy it is to react to user inputs in a clean and structured way using reactive streams. This approach encapsulates event handling within a reactive framework, offering a powerful mechanism to manage user interactions in web applications. Now let's take a look at how we can implement error handling in observables using the RxJS library. In this example, we create an observable called fetchDateObservable, designed to simulate a failed data fetch operation by invoking the subscriberError method, which emits an error. This demonstrates how observables can handle errors gracefully compared to traditional methods. Next, we pipe the observable through the catchError operator, which allows us to intercept any errors that occur. Within this operator, we log the error message to the console, which provides insight into what went wrong. Importantly, we return a fallback value using the of operator, which emits a predefined value, default data, ensuring that our observable can still emit a valid value despite the initial error. When we subscribe to the fetchDateObservable, we handle the emitted data in the next callback, which logs the received data to the console. The error callback will not execute in this case because we've already managed the error with catchError. This approach highlights how RxJS facilitates a clean syntax for error handling while maintaining a functional programming style, enhancing the robustness of our asynchronous operations. Now let's implement the following example to demonstrate how to share subscriptions using observables efficiently. In this code, we create a new observable called sharedObservable that emits a random number. The observable execution is wrapped with a function that logs creating observable to the console whenever it is invoked. This highlights that the observable is designed to perform a single execution, regardless of how many subscribers there are. Now, by applying the share operator from RxJS, we ensure that the observable's execution is shared between multiple subscribers. This is particularly beneficial in scenarios where you want to avoid duplicate resource-intensive operations. When we subscribe to sharedObservable for the first time, the random number is emitted to the first subscriber and logged to the console. When a second subscriber joins, it receives the same emitted value without re-executing the observable's creation function, brilliantly demonstrating resource management and efficiency in handling multiple subscriptions. This feature is a key advantage of using observables, as it enables multiple parts of an application to react to a single data stream without incurring additional overhead. Now let's see how we can implement a custom operator to filter out even numbers from an observable stream. We start by importing the necessary observable class and the filter operator from RxJS. The oddNumbers function is defined as a custom operator, which will take an observable of numbers as its source and return a new observable. Inside this function, we utilize the filter operator to pass only the numbers that are odd, effectively removing any even numbers from the emitted sequence. Next, we create a new observable called numbers$, which emits a sequence of numbers from 1 to 10. This observable employs a subscriber to generate the values, which will be sent to any observers once the observable is activated. Now, by piping the oddNumbers custom operator into numbers$, we can process this stream and filter out the even numbers seamlessly. When we subscribe to this modified observable, each odd number emitted will trigger the provided next function, allowing us to log only odd numbers to the console. This demonstrates how custom operators can enhance code modularity and clarity in handling streams of data in a reactive programming context. Now let's implement a simple counter state using a behavior subject. The behavior subject is an observable that stores the current value and emits it to any new subscribers immediately. This feature is particularly useful in UI-driven applications where state needs to be readily available and updated dynamically. In our example, we initialize a behavior subject with a starting value of 0, effectively setting our counter to its initial state. As part of the implementation, we subscribe to the counter $observable. This subscription allows us to react to value changes within the counter. Specifically, we log the current counter value to the console each time it updates. Next, to increment the counter, we call the next method on counter while retrieving the current value with getValue. This operation updates the counter by adding 1, demonstrating how we can manipulate state behaviorally. By invoking next twice, we showcase how easily we can change the state and reflect these changes throughout our application. This approach exemplifies the power of observables in managing dynamic application states effectively. To sum up, observables provide an incredibly powerful model for managing asynchronous data flows in TypeScript applications. Using observables via the ReactiveX library enables developers to elegantly handle events, time-based updates, and data changes. Through creating basic observables, combining them, handling errors, and managing state, we can build reactive applications that are both efficient and easy to maintain. As we wrap up today's discussion, remember that embracing observables will significantly improve your coding practices and applications. They open up a world of possibilities in asynchronous programming, encouraging a cleaner, more functional approach. In our next video, we will explore more advanced topics within reactive programming and how to integrate them into scalable applications. Stay tuned and Implementing domain-driven design, or DDD, represents an approach to software development that effectively translates complex business logic into software components that accurately reflect their meaning and purpose. In this session, we are going to dive deep into how to implement DDD in your projects. Fasten your seatbelts and let's get started. So far, we learned about foundational concepts such as promises, async-await patterns, and observables, which empower us to manage asynchronous operations effectively. Now, we will cover how to structure our software architecture using domain-driven design to create models that align with vital business needs. Now let's explore how we can implement a basic shopping cart in TypeScript using the concepts of domain-driven design. In our implementation, we define a cart class, which serves as the main structure for holding items. This class contains a private property called items, which is an array that will store instances of cart item. By keeping this property private, we encapsulate the internal state of our cart, ensuring that it can only be modified through the class's methods. Inside the cart class, we have an addItem method that allows us to add cart item instances to our cart. This method takes a cart item as an argument and pushes it into the items array, effectively altering the state of the cart without exposing the direct manipulation of the items. Furthermore, we implement a calculateTotal method, which computes and returns the total price of all items in the cart. It achieves this by using the reduce function to iterate over the items array, summing up the price property of each cart item. We also define a cart item class, representing individual items in the cart. This class includes a constructor that initializes the name and price of the cart item, allowing us to create instances that have relevant attributes. By structuring our code this way, we clearly separate the concepts of the shopping cart and the items it contains, promoting better organization and easier maintenance, which are key aspects of domain-driven design. Now let's see how we can define our entities within the context of user management and payment processing, which are crucial for our e-commerce application. We start by creating an interface for the user, which includes essential properties such as ID and email. This structure ensures that every user within the system has a unique identifier and a means of communication, which are vital for functionalities like account verification and personalization. Next, we proceed with the payment interface, which outlines the necessary attributes for processing transactions. This interface consists of an amount to represent the transaction value and a method to specify how the payment is made, such as through a credit card or a digital wallet like PayPal. By defining these interfaces, we establish a clear and shared vocabulary that is crucial for productive collaboration between technical and business stakeholders. Such clarity helps prevent miscommunication as the application scales, allowing developers to work effectively with domain experts while ensuring that the software aligns with business needs. This foundational work sets the stage for further aspects of our design and implementation in domain-driven design. Now let's see how we can define our model by introducing the user and address classes. the user class is an essential entity within our e-commerce application, equipped with a constructor that takes two properties, a unique identifier id and a name. This structure allows each user to be distinct, enabling them to interact with different parts of the application while retaining their unique identity. On the other hand, the address class serves as a value object in our domain. Unlike entities, value objects do not possess a unique identity and are defined solely by their attributes. In this case, address encapsulates the properties of a physical location, including street, city, and postal code. This means that multiple instances of address can be considered equal if they share the same values for these attributes. By structuring our model in this way, we ensure clarity in how different parts of our application relate to each other, adhering closely to the principles of domain-driven design. This encapsulation of behavior and identity helps maintain a cohesive understanding of the domain and supports aligning our code with the evolving business requirements. Now let's take a look at the user repository class, which serves as an essential component in managing user data while adhering to the repository pattern in domain-driven design. This class encapsulates all operations related to user instances, providing a clean interface to interact with the data without exposing the underlying database logic. The user repository class starts with a private array called users, which acts as the in-memory storage for user objects. This encapsulation keeps user management logic tightly bound to the repository, enhancing modularity and maintainability. Next, we have the adduser method, which accepts a user object and appends it to the user's array. This method ensures that adding a user is managed in one place, simplifying the code later and allowing for expanded functionality, such as validation or logging, in the future. Additionally, the findUserById method enables us to retrieve a user based on their unique identifier. It uses the JavaScript array method, find, which returns the first user matching the specified ID or undefined if no match is found. This encapsulated approach not only abstracts the data handling, but also facilitates reliable unit testing by allowing us to mock the user repository during tests. Together, these methods promote a clean separation of concerns in our application architecture, aligning with the principles of DDD. Now let's take a look at the Event Dispatcher class, which plays a crucial role in managing domain events within our application. This class allows us to decouple different components by enabling them to react to specific events in isolation. The Event Dispatcher maintains a private listeners object, where events are mapped to their respective listener functions. To register a new listener for a particular event, we use the addListener method. This method checks if there are already listeners for the event. If not, it initializes an empty array for that event. Adding listeners is as simple as pushing the provided listener function into the appropriate array. Next, we can trigger these listeners using the dispatch method. When an event occurs, we call dispatch, passing in the event name and any relevant data. This method checks if there are listeners associated with the event, and if they exist, invokes each listener function with the provided data. This setup allows for flexible communication within our application, ensuring that various components can respond dynamically to significant actions, such as user registrations or updates in the system. By implementing this pattern, we enhance both the scalability and maintainability of our code. Now, while implementing DDD can offer significant advantages, it comes with its own set of challenges. One major consideration is that DDD is highly dependent on the availability of domain experts. If your team lacks domain knowledge, it can become challenging to develop a model that accurately captures the domain's intricacies. Therefore, investing time in understanding the domain thoroughly and fostering strong communication between business and technical teams is essential. Additionally, the initial setup for a DDD approach can require considerable investment in time and resources, particularly for establishing ubiquitous language and refining domain models. However, in complex domains, the benefits outweigh these initial costs, as DDD leads to more maintainable and adaptive software systems. In conclusion, implementing domain-driven design is no small feat. It entails understanding the business domain, establishing a clear vocabulary, structuring your models around entities and value objects, and managing domain events effectively. Each of these components is crucial for creating software that not only meets current needs, but remains flexible to adapt to future changes. While DDD may require significant upfront investment, it lays down a solid foundation for software that resonates deeply with business objectives. So there you have it. We've covered the vital components of domain-driven design and how to implement them in TypeScript. Hopefully, this lecture provided you with insights to help you develop applications that reflect the real-world complexities of your business. you now have the tools to create meaningful and manageable software solutions that grow alongside the needs of the domain. That wraps up our discussion on implementing domain-driven design. Don't forget to check back in as we dive more into practical techniques for developing robust applications in TypeScript. SOLID is an acronym for the first 5 object-oriented programming (OOP) design principles that enhance flexibility, maintainability, and scalability in software development. Today, we will dive deep into these principles, exploring what they entail and how to implement them in TypeScript, ensuring that we write clean, efficient, and robust code. So far, we learned that domain-driven design, DDD, is a methodology focused on accurately reflecting complex business logic in software through concepts like bounded contexts and ubiquitous language. We explored key components like entities, value objects, repositories, and domain events that help structure our applications more effectively. While implementing DDD can pose challenges, including the need for strong domain knowledge, its benefits in creating maintainable and adaptable software make it worthwhile. Overall, DDD equips us with the tools to align our development processes closely with business needs. Now, we will cover the essential SOLID principles in detail. Now let's see how we can implement the Single Responsibility Principle, SRP, using a simple example. We start by defining a user class, which encapsulates user-related data, specifically the user's name and email. This class serves a single purpose, to represent user information, promoting clarity and maintainability. Next, we introduce a separate class, User Notifier, responsible solely for sending user notifications. In this case, it has a method called sendWelcomeEmail, which takes a user instance as an argument and logs a message indicating that a welcome email has been sent to the user's email address. By segregating concerns in this manner, we demonstrate adherence to SRP, as each class now has a distinct responsibility. This approach allows for easier modifications. If we need to change the notification logic, we can do so within the User Notifier class without affecting the user class. Consequently, improvements in maintainability and readability arise, enabling developers to work on specific functionalities without the risk of unintentional side effects in other areas of the code. Next, we will implement the Open-Closed Principle, OCP, using an example involving geometric shapes. We start by defining a shape interface that declares a method called area, which any implementing class must define to calculate its area. This interface establishes a contract for all shapes, ensuring they provide a way to calculate their area without dictating how that should be done. Now let's see how we can create specific shapes by implementing the shape interface. We define a circle class that takes a radius as an argument and implements the area method using the formula for the area of a circle. In parallel, we create a rectangle class that requires width and height to compute its area in a straightforward manner. Next, we introduce an area calculator class, which demonstrates the power of polymorphism. This class contains a method called calculateTotalArea that takes an array of shapes and calculates the total area by calling the area method on each shape instance. This design allows us to add new shapes, like a triangle, in the future without modifying the area calculator class. Thus, we adhere to the OCP, enabling our code to extend its functionality seamlessly. Now let's explore how the Liskov substitution principle can be implemented in our code. We start by defining a base class called bird, which has a method fly. This method outputs a message indicating that the bird is flying high. From this base class, we create 2 subclasses, eagle, which inherits the flying capability without modification, and penguin, which overrides the fly method. However, in the case of penguin, the method throws an error because penguins cannot fly. This violates the Liskov substitution principle, as substituting a penguin for a bird leads to an unexpected consequence. To address this issue, we can redesign our approach by introducing an interface named Flyable. The Eagle class will implement this interface to ensure it has a fly method. On the other hand, the Penguin class won't implement Flyable, as it does not fly. By doing so, we separate flying birds from non-flying birds while ensuring that all subclasses adhere to their base class's contract, thus maintaining code integrity and promoting adherence to the Liskov substitution principle. This approach improves the clarity and functionality of our code. Now let's take a look at how we can better structure our printing functionality by adhering to the interface segregation principle. Initially, we have a printer interface that defines 3 methods: print, scan, and fax. This kind of broad interface can lead to complications, especially if a class implementing it, like SimplePrinter, only needs 1 or 2 of these methods. In this case, SimplePrinter implements all methods, but it throws errors for the unsupported functionalities. To resolve these issues, we break down the printer interface into smaller, more focused interfaces, printable and scannable. Each new interface has a single responsibility, ensuring that any class can implement only what it needs. For example, the revised simple printer simply implements the printable interface, which requires it to define the print method. This change not only cleans up our code by removing extraneous dependencies, but also enhances its readability and maintainability. By allowing classes to implement only relevant interfaces, we promote a more efficient coding practice that aligns with the principles of clean software design. Now let's explore how we can implement the dependency inversion principle, DIP, in our design. We start by defining an interface named userRepository, which declares a method getUserById. This interface serves as an abstraction for any class that will implement user retrieval functionality, ensuring a clear contract for behavior without tying our code to a specific implementation. Next, we create a class called DatabaseUserRepository that implements the userRepository interface. Within this class, the method getUserById retrieves user data from the database. By utilizing this approach, we isolate our data access logic and adhere to the DIP, allowing flexibility in how we handle user data. Now let's take a look at the userService class. This class is initialized with a userRepository, showcasing that it does not depend directly on low-level implementations. Instead, it operates with the abstraction provided by the interface. The fetchUser method calls getUserById, showcasing how userService uses the abstract concept of a repository rather than being tied to a specific data access method. This design pattern fosters better testability and maintainability, allowing for easier updates or changes to the underlying data retrieval methods without impacting the user service. In summary, embracing the solid principles helps us develop software that is easier to manage, extend, and maintain. By following these principles, single responsibility, open-closed, list-of substitution, interface segregation, and dependency inversion, we can create cleaner and more efficient code that not only serves our current business needs, but is also resilient to changes in the future. By applying these principles in your TypeScript projects, you'll build a robust architecture that can gracefully accommodate evolving requirements. Remember, the goal isn't just to write code that works, but to craft software that is elegant and maintainable over time. So as you continue coding, keep solid principles in mind to guide your design decisions and improve the quality of your software. Just as there are good design patterns and best practices when using TypeScript, there are some anti-patterns as well. Anti-patterns can lead to less readable, maintainable, and scalable code, making them problematic for developers. In this lesson, we'll take a closer look at some common anti-patterns in TypeScript, understand why they are considered bad practices, and explore how to avoid them. So far, we covered the solid principles, highlighting their importance in creating flexible and maintainable software through key concepts like single responsibility and dependency inversion. Now we will cover anti-patterns in TypeScript, diving deep into their implications and offering solutions to make our code cleaner and more efficient. Next, we will look at a common pitfall in TypeScript programming, using the any type. In the first code snippet, we declare a variable named value with the type any. This allows value to hold any type of data, as demonstrated when we assign it a string, hello world, and later an integer, 42. While this approach seemingly works fine and provides flexibility, it completely bypasses TypeScript's type safety, leaving us vulnerable to runtime errors that could have been caught at compile time. Now let's see how we can enhance our code by replacing any with a union type. In the second snippet, we redefine value as a combination of types, specifically string or number. This ensures that value can only hold either a string or a number. Thus, when we assign hello world or 42 to value, we remain within the bounds of type safety. This approach not only clarifies our intent as developers, but also aids TypeScript's compile time checking, which catches type-related errors before the code is executed. Embracing specific types enhances maintainability and reduces the likelihood of bugs in our applications. Now let's examine the implications of using non-null assertions in TypeScript. The first example uses the non-null assertion operator to forcefully indicate that a value, which could possibly be null, will be treated as a valid string. While this might seem convenient, it can lead to runtime errors if the value is indeed null when the code executes. Therefore, it's essential to be cautious with such assertions, as they could introduce significant risks into your application. Next, we will write a safer implementation that checks whether the value is null before performing any operations. Here, we introduce a conditional statement that verifies the value's existence. If the value isn't null, the code proceeds to safely access the length of the string. Otherwise, it logs a warning message, allowing for better error handling and maintaining the application's robustness. This approach emphasizes the importance of input validation in our functions, ensuring that we avoid unexpected crashes and create a more reliable code base. Always prioritize safety checks over assertions to enhance code quality. Now let's take a look at a common example of spaghetti code in TypeScript, which showcases a class that is responsible for multiple unrelated functionalities. The user class is designed to manage a user's details, such as their name and age, while also including methods for updating the user's age, sending emails, and logging user information. This mix of responsibilities violates the single responsibility principle, which states that a class should only have one reason to change. Next, we will write a refactored version that separates concerns to enhance maintainability and clarity. We'll create a user class that strictly manages user details and a separate email service class solely for sending email notifications. This method not only clarifies the purpose of each class, but also allows for easier testing and debugging. By adopting this organized approach, we improve the code structure, making it simpler for future developers to navigate and onboard. This shift encourages a cleaner, modular design that aligns with best practices in software development, ultimately resulting in a more scalable and efficient code base. Now let's take a look at a common way to define a user structure in TypeScript using an interface. In the first example, we define a simple user interface that includes properties such as name, age, and email. This approach outlines a clear contract for any object that claims to be a user, ensuring that all user objects contain these essential attributes. By creating a user object based on this interface, we leverage TypeScript's type checking, which helps prevent errors and provides clarity in our code. Next, we will explore a more sophisticated implementation by defining two interfaces, Basic User and Admin User. The Basic User interface retains the fundamental properties, while Admin User extends Basic User by adding additional properties such as email and permissions. This illustrates TypeScript's support for inheritance in interfaces, allowing for more granularity and specificity in our type definitions. With this structure, we can enforce stricter typing across different user roles, leading to safer and more organized code that accurately represents the varying data shapes within our application. Now let's see how we can implement proper error handling in our data fetching function. In the initial version of our code, we attempted to fetch data from an API without considering potential failures, such as network issues or server errors. This oversight can lead to unhandled exceptions, crashing the application and providing no feedback to the user. To improve this, we wrap the fetch call in a try-catch block. This structure allows us to effectively manage any errors that occur during the fetch operation. In the try section, we attempt to retrieve the data, checking if the response from the API is okay. If it isn't, we throw an error with a clear message regarding the HTTP status. In the catch block, we handle any errors that may arise during the execution of the try code, logging a user-friendly error message to the console, instead of letting the application fail silently. This approach not only enhances the robustness of our code, but also significantly improves the user experience by signaling issues gracefully, thereby adhering to best practices in error handling. Now let's take a look at how we can structure our code using both inheritance and interfaces. First, we have a basic class called animal, which includes a method move that logs a message indicating that the animal is moving. Moving forward, we create a more specific class called mammal that extends animal, introducing the giveBirth method, which reflects its biological function. Then we refine our hierarchy further with the dog class, which extends mammal and adds the bark method to give it specific canine behavior. However, while this inheritance structure looks organized, it can become cumbersome as more subclasses are added, potentially leading to deeply nested hierarchies that are challenging to manage. To counter this, let's implement a more flexible approach through interfaces. For instance, we define a canine interface that requires the bark method. The dog class then implements this interface, reinforcing its canine characteristics. Additionally, we introduce a fish class that showcases a different type of behavior, swimming, demonstrating how composition and interfaces can facilitate a more modular and adaptable coding practice, moving away from excessive reliance on deep inheritance hierarchies. So there we have it, a deep dive into some common anti-patterns in TypeScript. We covered how overusing the any type can lead to a loss of type safety, the dangers of using non-null assertions blindly, and the pitfalls of spaghetti code, interfaces, poor error handling, and deep inheritance hierarchies. Each of these anti-patterns can significantly affect the maintainability and understanding of your codebase. By recognizing these pitfalls and adhering to best practices, you'll be on your way to writing cleaner, more efficient TypeScript code. Remember, the goal of any developer should be to create software that is not only functional, but also easy to read, maintain, and scale. Thank you for joining me in this exploration of anti-patterns. Let's apply this knowledge in our future coding. Now let's define the structure of our book model using an interface. We start by creating an interface named book, which lays out the essential properties that any book object must possess. This interface specifies that each book should have a title and author as strings, a published year as a number, and a genre also as a string. By using an interface for this definition, we ensure that any object considered a book will adhere to this predefined structure. This not only helps in establishing clear contracts within our code, but also adds a layer of type safety. Whenever we declare an object as a book, TypeScript will verify that it includes all the required properties, helping to catch potential errors early in the development process. This approach also keeps our code organized and manageable, especially as our application scales, allowing for easy modifications or enhancements in the future. Now that we've set up our book interface, we can implement various book objects that conform to this design, maximizing both reusability and clarity in our code. Now let's see how we can implement the book interface with specific objects that follow its defined structure. We create two objects, Book 1 and Book 2, which represent different books. Each object is assigned to the book type, ensuring that it has the required properties: title, author, published year, and genre. This not only adheres to the book interface, but also guarantees that any future modifications or functionalities we want to introduce around books can utilize these objects seamlessly. Next, we will write a function called printBookDetails that takes a parameter of type book. This function demonstrates how we can work with objects aligned with the book interface effectively. Inside the function, we access the properties of the book parameter and log its details to the console in a readable format. Finally, we call this function with both Book 1 and Book 2, showcasing how easily we can operate on different objects that comply with the same interface without duplicating code or adding complexity. This implementation highlights the power and flexibility of interfaces in promoting a clear and consistent structure in our applications. Now let's take a look at how we can build upon the book interface to create a more specialized type of book. We start by defining a new interface called Educational Book that extends the existing book interface. This extension allows us to include two additional properties, subject and level, which are specific to educational materials. By extending the base interface, we maintain a clear structure while adding more detailed attributes without complicating our codebase. Next, we will implement this new Educational Book interface by creating an object named Book 3. This object conforms to both the book interface and the newly defined Educational Book interface. It includes all the required properties from books such as title, author, published year, and genre, while also featuring the new properties subject and level, which enrich its definition. This approach illustrates the power of interfaces in TypeScript, as it enables us to create a detailed and organized structure while ensuring that all necessary properties are present. By adhering to this interface structure, developers can easily understand the data's expected format, enhancing both clarity and maintainability in complex applications. Now let's take a look at how we can implement a library catalog feature using interfaces in TypeScript. We begin by defining a library interface, which outlines the structure of our library, including a books array that will hold our collection of book objects and a method called addBook, designed to add new books to this collection. This clear separation of concerns allows us to focus on what operations we need without worrying about the underlying implementation details. Next, we create a class called MyLibrary that implements the library interface. Inside this class, we initialize the books array and provide the implementation for the addBook method, which simply pushes the new book onto the books array. With this structure, MyLibrary adheres to the rules set out by the library interface while maintaining flexibility in managing its books. Now let's see how we can utilize this setup by creating an instance of MyLibrary. We can then add various book objects, such as Book 1, Book 2, and Book 3, to our library without needing to alter the class implementation. This demonstrates the power of interfaces in enabling easy scalability and adaptability in our codebase. Now let's implement the interface for user feedback to reinforce our understanding of type safety in TypeScript. We start by defining a feedback interface that specifies the required structure for feedback objects, ensuring that they include properties for the user's name, email, and the feedback message. This design choice is crucial as it establishes a clear contract for any objects that will be used to capture user feedback, making sure they adhere to this structure. Next, we write a function named handleFeedback that takes an argument of type feedback. This function uses template literals to log a message containing the feedback details to the console, clearly demonstrating how we can safely access the properties defined in the interface. By utilizing TypeScript's type checking, if a developer mistakenly attempts to pass an object that lacks the requisite properties, TypeScript will raise a compilation error. This proactive error handling not only simplifies debugging, but also enforces a more disciplined approach to coding, ultimately leading to fewer runtime issues and a more robust application. Now let's implement the following interface that includes optional properties. Here, we define an interface named Book with Optional Fields, which specifies that a book must have a title and an author, while also allowing published year and genre as optional properties. This means when creating a book object, you can include these optional fields if they are relevant, or omit them if they are not available at the time of object creation. Next, we create an object named Partial Book that conforms to the Book with Optional Fields interface. In this example, we've provided only the required properties, title and author. Notice how we did not include published year or genre, accentuating the flexibility afforded by optional properties. TypeScript recognizes and allows this partial implementation while ensuring that we adhere to the defined interface's core structure. This feature is particularly beneficial for scenarios where certain attributes might not always be known upon object creation, enabling developers to build up their data models seamlessly over time. As we wrap up our discussion on using interfaces for models in TypeScript, it's crucial to recognize the advantages they provide over traditional class-based models. With interfaces, you gain flexibility, scalability, and clarity. They help enforce the integrity of your code while allowing for easy collaboration among teams and reducing the chances of runtime errors. In summary, utilizing interfaces when defining models in TypeScript can lead to cleaner, more maintainable, and scalable codebases. You can create flexible data structures while ensuring type safety and adherence to specific contracts. By leveraging the capabilities of interfaces, you'll embrace a more organized approach to developing applications, paving the way for smoother development experiences. Thank you for joining me in this exploration of using interfaces for models. Remember, a well-defined model is the cornerstone of any robust application. Now go out there and start crafting your own elegant TypeScript models using interfaces. In this segment, we will dive into the fascinating world of Apollo Client and Trpc. Both of these technologies are prominent in modern web development, tailored for handling data fetching needs in various applications. With that, you'll discover their unique strengths and how they can empower your TypeScript projects. So far, we explored the advantages of using interfaces over classes in TypeScript for defining models. We emphasized flexibility, scalability, and maintainability, highlighting how interfaces foster clear structure for objects while promoting code reusability and enhancing type safety. Moving forward, we will cover Apollo Client and Trpc, illuminating why they are essential tools in your development toolkit. Now let's implement the code that initializes Apollo Client in our TypeScript application. We start by importing the essential components: Apollo Client, in-memory cache, and Apollo Provider from the Apollo Client library, along with React and React DOM to handle our application structure. This setup is critical as it allows us to connect our React application to a GraphQL endpoint efficiently. Next, we create an instance of Apollo Client, where we specify the URI of our GraphQL endpoint, which in this example is a placeholder and should be replaced with your actual endpoint. The in-memory cache is an essential feature here, enabling the client to store query results locally. By caching these results, we minimize unnecessary network requests, thereby enhancing performance and user experience. After configuring the client, we use React DOM render to render our main app component wrapped in the Apollo provider. This provider supplies our application with access to the Apollo client instance, allowing us to use GraphQL queries and mutations throughout the application seamlessly. With this setup in place, your React app is now equipped to communicate with the GraphQL API effectively. Now let's implement a GraphQL query to fetch user data using Apollo Client's useQuery hook. We begin by defining a GraphQL query, getUsers, with the GQL tag, specifying that we want to retrieve the user's ID, name, and email. This structured query allows us to pinpoint exactly the data we need from the GraphQL API. Next, within our UsersList component, we utilize the useQuery hook to execute the getUsers query. The hook returns three important properties: loading, error, and data. The loading property indicates whether the data is currently being fetched, letting us provide user feedback, such as displaying a loading message. If an error occurs during the fetch, the error property provides details, enabling us to handle it gracefully by presenting an error message to the user. Upon successful data retrieval, we access the data property, which contains our users. we iterate over the list of users, rendering each user's name and email within an unordered list. This approach not only keeps our UI interactive and responsive, but also demonstrates a clean and efficient way to handle data fetching in a React application using Apollo Client. Now let's implement the Trpc server setup to facilitate our API communication. First, we use the createRouter function from the @trpc/server package to define our application's router, named approuter. Within this router, we can define various API endpoints, starting with a single query called getUser. This query expects a string input, which represents the user ID. As we move into the resolve function, we simulate the process of fetching user data by returning a hard-coded object containing an ID, name, and email address. In practice, this is where you would incorporate your database interaction logic or service layer to retrieve actual user data. Importantly, we also include the usage of zstring to validate the input type, enhancing the type safety of our API. Lastly, we export the approuter type derived from our approuter, allowing TypeScript to infer types based on our defined roots, which helps maintain consistency and reduces potential errors throughout the application. This setup is a crucial step in establishing clear and safe communication between the front-end and back-end in a Trpc-based project. Next, we will implement the Express server that integrates with our Trpc setup. First, we import necessary modules, including Express, Trpc's utilities, and our defined router. We begin by defining a context creation function, which serves to manage shared data between requests, although we leave it empty for now. This flexibility allows for customization later on if needed. Then we initialize Trpc with the context type, setting up our server-side structure. We create an Express application using the Express function, enabling us to define routes and middleware. At this point, we integrate Trpc by applying its middleware specifically for the /trpc endpoint, which is crucial for routing requests to our defined API queries. Finally, we instruct the server to listen on port 4000, providing a console log to confirm that our server is up and running. This setup serves as the backbone for our Trpc API, allowing front-end applications to interact seamlessly with our backend logic while maintaining the benefits of TypeScript's type safety and structure. Now let's see how we can implement the user retrieval functionality using the Trpc client in a React component. In this code, we define a functional component called user, which takes a userid as a prop. Within this component, we utilize the Trpc useQuery hook to execute the getUser query, passing in the userid as an argument. This hook manages the fetching process and returns an object containing the loading state, any errors encountered, and the retrieved data. When the component first renders, the userQuery object will indicate that the data is still loading, prompting us to display a loading message to the user. If an error occurs during the fetch, we handle it gracefully by showing the error message instead. Once the data is successfully retrieved, we can access the user's name and email from userQuery data, allowing us to display this information in the component. This structured approach not only ensures that our user interface remains responsive, but also leverages TypeScript's type inference, reducing potential errors and improving the overall development experience. Both Apollo Client and Trpc offer compelling solutions for data fetching within TypeScript applications, each with its distinct advantages. Apollo Client shines in managing GraphQL data with a rich set of tools and caching strategies, whereas Trpc excels in simplicity and type safety, streamlining the API development process. As a developer, choosing between these two technologies ultimately depends on your project requirements and personal preferences. In this lesson, we delved deep into Apollo Client, exploring its setup, data fetching patterns, and integration within a React application. We then transitioned to Trpc, examining its unique capabilities and how it facilitates type-safe API development. By understanding both technologies, you're now equipped to make informed decisions for your future TypeScript projects, enhancing both your productivity and the robustness of your applications. As you continue your journey through TypeScript and backend interactions, remember to implement best practices such as structuring your code with clarity, keeping your components manageable, and ensuring type safety at all levels. Engaging in forums and discussions can further enhance your learning experience, providing insights from the developer community and new ways of approaching challenges. Let's dive into the fascinating world of design patterns within Trpc and Apollo Client. Understanding these patterns is essential for crafting solid, maintainable applications that not only perform well, but are also easy to scale and enhance over time. In this session, we'll explore the unique patterns these tools facilitate, enabling you to optimize your TypeScript applications. So far, we learned about Apollo Client and Trpc, two powerful technologies for data fetching in TypeScript applications. We explored Apollo Client's capabilities for managing GraphQL data and its integration into React, followed by an introduction to Trpc, which allows for type-safe API development. We highlighted the distinct advantages of both tools, emphasizing their roles in enhancing developer productivity and application robustness. As we move forward, we will cover design patterns that enhance functionality in Apollo Client and Trpc, allowing us to leverage their full potential. Now let's see how we can implement the container component pattern using Apollo Client. We begin by importing the necessary dependencies from React and Apollo Client, including the GQL function for defining our GraphQL queries and the useQuery hook for executing these queries within our component. Next, we define a GraphQL query called getUsers, which retrieves a list of users with their associated details, such as id, name, and email. This query will serve as the foundation of our data fetching logic. Now let's implement the user container component, which will utilize the useQuery hook to fetch the data from the GraphQL server based on our defined query. The useQuery hook provides us with the loading state, error messages, and the fetch data. We immediately handle the loading and error states to improve user experience by showing appropriate messages while the data is being fetched. Once the data is successfully retrieved, we pass the user information down to the userList presentational component, ensuring a clean separation of responsibility. This structure not only enhances code readability, but also maintains ease of testing and future scalability. Now let's see how we can implement a higher-order component, HOC, with Apollo Client to enhance our components with additional functionalities like data fetching. We start by importing the necessary libraries and defining a GraphQL query to fetch user data, which includes the user's ID, name, and email. Next, we create the withUsers HOC, which takes a React component as an argument and returns a new component. This return component allows us to pass down any props it receives unaltered to the wrapped component. This setup provides a clean abstraction layer for injecting user data into your components without altering their internal logic. Finally, we wrap our userList component with the graphical function from Apollo Client, applying the getUsers query through our withUsers HOC. This effectively enhances userList with user data while maintaining separation of concerns. By using this pattern, we can easily reuse the logic across multiple components, promoting code maintainability and enhancing the overall structure of our application. Now, let's explore the implementation of a user service in Trpc. This service encapsulates the business logic related to user management, allowing for a more modular and organized codebase. We begin by importing necessary modules, including Zod for schema validation and the user model. The user service object contains methods to handle user-related operations. The getUser method takes an id as a parameter and performs an asynchronous operation to fetch the corresponding user from the database. If the user is not found, it throws an error, ensuring that our application can gracefully handle missing data. Next, we have the createUser method, which also performs an asynchronous task. This method accepts data validated using a schema defined by Zod, ensuring that the input conforms to expected types before interacting with the database. If successful, it creates and returns a new user. By structuring your logic in this way, you achieve greater code stability and maintainability. Any future changes in user management, whether fetching or creating users, can be handled in one centralized location, making your code easier to test and update. Next, we will write the code that defines a user router in Trpc using the createRouter method. This router will encapsulate our API logic for user-related actions, organizing it effectively for scalability and clarity. Now let's take a look at the getUser query defined within the router. This query takes a single string input which represents the user ID. When executed, it resolves the input asynchronously and invokes user service, getUser input, retrieving the corresponding user data. This structure allows for clear input validation and ensures we handle user retrieval efficiently. Next, we will implement the createUser mutation in a similar manner. This mutation also includes input validation, but in this case, it utilizes a schema defined by createUser schema to ensure the data format is correct. Upon execution, this mutation will call user service, createUser input, allowing us to create new users seamlessly. Overall, this design pattern promotes type safety and modularity, making it easier to maintain and extend our API in line with TypeScript best practices. Now let's take a look at how we can implement robust error handling in our Trpc procedures. The first step involves importing the Trpc error class, which enables us to create custom error messages for our application. In this example, we define a user router that processes a query for fetching a user by their ID. The procedure specifies the expected input type as a string, ensuring that we adhere to proper type safety. When resolving the query, we attempt to retrieve the user through our user service. If the user is not found, instead of returning a generic error, we throw a Trpc error with a specific code and a meaningful message that indicates exactly what went wrong, namely, the absence of a user with the given ID. This approach not only centralizes our error handling, but also enhances the user experience by providing clear feedback. By using custom error classes like Trpc error, we maintain uniformity across our application's error management, making it easier to debug and ensure a consistent handling process for application-level errors. This design pattern significantly contributes to building a robust and maintainable application with clear error messaging. Next, we will implement a custom error handling mechanism in Apollo client to enhance our data fetching process. The function fetchUsers is designed to asynchronously retrieve user data from the GraphQL server. Inside this function, we utilize a try-catch block to manage potential errors that may arise during the query execution. Initially, we make a call to the Apollo client to execute the getUsers query, which fetches the user's data. If this operation is successful, the function returns the list of users. However, if the operation encounters an error, the catch block is triggered. Here, we log the error details to the console, providing visibility into what went wrong during the data fetching. It's crucial in debugging processes, especially during development. Moreover, we throw a new error with a user-friendly message, ensuring that any component attempting to fetch users can handle this gracefully. This abstracted error handling keeps the focus on business logic in our components, improving the overall readability and maintainability of the code. This pattern promotes a consistent approach to error management across our application. Now let's take a look at how we can effectively manage state updates in Apollo client using its caching features. The adduser function demonstrates how to handle a user addition through a mutation. When a new user is created, we first await the completion of the mutation defined by add_user, which sends data to the server. Next, we utilize the update function provided in the mutation options to manipulate the cache directly. This is a crucial step because after the mutation, we need to ensure the UI reflects the latest data without fetching it from the server again. Here, we read the existing users from the cache using cacheReadQuery with the getUsers query. Once we have the current state of users, we blend the newly added user into this array and update the cache using cacheWriteQuery. This approach enables the application to maintain responsiveness and performance by ensuring that the UI remains in sync with the cache data, eliminating unnecessary network requests and enhancing the overall user experience. Now let's implement a way to manage user data through context in our Trpc application. We begin by creating a user context using React's Context API, which provides a centralized way to share data across components without the need to pass props down manually at every level. This context starts with an initial state that includes an empty list of users, a loading state set to false, and a potential error state initialized to null. Next, we create a user provider component that utilizes React Query to fetch user data. By calling useQuery, we define a query with the key users and a function that fetches users through our Trpc setup. This hook automatically manages loading and error states for us, making the process of handling asynchronous data efficient and effective. As the data comes in, we pass the fetched users, the loading status, and any error messages into the context provide as value. This approach allows any child component that consumes the user context to access user data, monitor loading states, and handle errors appropriately. Utilizing this pattern enhances our application's responsiveness and maintainability, allowing for a clean separation between data fetching logic and presentation. In conclusion, as we've explored design patterns in Trpc and Apollo client, we have uncovered various methodologies to enhance your applications. From the container component and higher-order component patterns in Apollo client to the procedure and service layer patterns in Trpc, each pattern has its unique use cases and benefits. We also touched on the significance of structured error handling and state management, both of which are crucial for developing robust applications. By mastering these design patterns, you position yourself to write cleaner, more efficient code while leveraging the best features each tool offers. Continue exploring these design patterns in your projects. By applying these principles thoughtfully, you'll create applications that are not only powerful but also maintainable and scalable. Enjoy the journey and keep. In this final section, we will do a project challenge to apply what we have learned so far. The objective of this project is to create a robust and scalable application using TypeScript design patterns. You will need to choose at least 3 different design patterns, such as creational, structural, and behavioral patterns, to effectively solve a real-world problem in your application. This could be a web app, a command line tool, or any software that demonstrates your understanding and application of the design patterns covered in the course. Your implementation must justify the use of each selected pattern and include thorough documentation explaining your design, architecture, and functionality. Additionally, rigorous testing must be conducted using a library of your choice, ensuring each pattern is validated through unit tests. You will also prepare a brief presentation to showcase your application, outlining the problem you are addressing, key features, and the benefits of the design patterns you have used. For more details and resources, refer to the final project in the GitHub repository linked in the description. Good luck, and have fun applying your knowledge to build something